On? Oh, it's on, yes. All right, welcome. We will begin our workshop. Thank you all for joining our workshop today on the role of carbon management on the path to carbon neutrality. We have an excellent lineup of panelists here, and they're all involved in research and planning and actually making things happen. We appreciate all the time and effort that you have put into that you've dedicated to the workshop. So here at CARB, we are here to listen and learn about the latest thinking around these areas, and we are looking forward to having this initial conversation about carbon capture, sequestration, and options for utilization. So first, just a couple housekeeping notes. Please note where the room exits are, and if we have a building alarm, we are required to evacuate. So please take your valuables, go down the stairs, and exit the building. Go across the street to the Cesar Chavez Park to await the all-clear signal. There is a drinking fountain and restrooms on this floor to the left as you go out of the room here. And there are food and beverages available in the cafeteria downstairs, but only for a little bit longer. They close in about half an hour. Oops, yes, sorry. So we encourage you to submit comments at the link that's shown in the screen, and the meeting can also be viewed on webcast. The webcast will be recorded, and it will be posted on this website as soon as we can. So this slide shows the impact of the key statutes and executive orders that guide the state's climate targets. In 2006, AB 32 set our initial 2020 target to return to 1990 greenhouse gas emission levels. Then SB 32 called for a 40% reduction in statewide greenhouse gas emission levels, emissions below 1990 levels by 2030. CARB's 2017 scoping plan lays out a cost-effective and achievable path for this target. This 2030 target is on the path to achieving the executive order goal of reducing greenhouse gas emissions 80% below the 1990 levels by 2050. And both last year's executive order calling for carbon neutrality by 2045 and the climate science presented in the IPCC's special report on 1.5 degrees Celsius require us to find ways to reduce greenhouse gases from fossil fuels, and they both emphasize our need to focus on sequestration opportunities. So carbon neutrality will require both reductions in greenhouse gas emissions and increases in carbon sinks. So our thinking about how to approach the climate challenge is evolving. The concept of carbon neutrality is gaining importance. The concept is that to address climate change, the carbon dioxide and other greenhouse gas emissions generated by sources such as vehicles, power plants, and industrial processes must be less than or equal to the amount of carbon dioxide that is stored both in natural sinks, such as forests, and by mechanical sequestration, such as through what we've known as carbon capture and sequestration. The magnitude of climate change impacts will depend on when carbon neutrality is achieved. In general, limiting warming to 1.5 degrees Celsius reduces climate-related risks and increases flexibility in mitigation and adaptation options. The IPCC's special report, released in late 2018, finds that to limit the global temperature increase to 1.5 degrees Celsius, we need to both reduce greenhouse gas emissions and remove carbon from the atmosphere. We need to reach global carbon neutrality by mid-century. The report also indicates that on a global scale, some regions may remain net emitters, while other regions are better suited as sinks. In California, we have an executive order that calls for carbon neutrality by 2045, consistent with the IPCC report. This executive order introduces the concept of balancing carbon emissions and carbon sequestration within the state. The framing of near zero emissions is not sufficient to meet the challenge laid out in the IPCC special report. We need our greenhouse gas emissions flux to be at zero or net negative, where we remove more carbon than we emit. The science is clear on where we need to be, and getting there will require contributions from all sectors. The path to carbon neutrality requires action on both sources and sinks. Today, we track statewide greenhouse gas emissions from transportation, electricity, commercial, residential, industrial, agricultural, and waste management sectors, including high global warming potential gases. We also track emissions and sequestration in our natural and working lands. Currently, these lands are a source of greenhouse gas emissions, releasing more carbon than they are sequestering. Some emissions from this sector are part of the natural cycle and are necessary for healthy systems, including emissions from periodic fires. Today, California emits greenhouse gas emissions from fossil energy and industrial sectors, as well as from our natural and working lands. To achieve carbon neutrality by mid-century, we must minimize emissions from our fossil energy and industrial sources to at least 80% below 1990 levels to achieve our 2050 goal. It's very likely that we will need to capture and sequester carbon from stationary sources as well. We also need to increase sequestration in our natural and working lands, and we likely need to find other ways to remove carbon directly from the atmosphere, using technologies such as direct air capture and sequestration. The framing of near zero emissions is not sufficient to meet the challenge. Oh, I'm sorry. Lost my place. Oh, dear. All right. At any point, like I said, we're aiming for the no net greenhouse gas emissions. So CARB recently adopted a landmark carbon capture and sequestration protocol under the low carbon fuel standard. The protocol allows credit generation for carbon dioxide that is captured from biofuel production, from crude oil and refinery operations, and through direct air capture. The LCFS program offers significant potential revenue for eligible projects and is attracting interest from several companies. The CCS protocol includes rigorous requirements to ensure accurate accounting and permanence of the carbon dioxide sequestration with monitoring for 100 years post-injection. Both the capture facility and the storage facility must be co-applicants to ensure that all entities are legally responsible for permanence. So we're holding this series of workshops, and this is one of the workshops, to provide a forum to initiate dialogue and gather information to assess potential actions that were identified in the scoping plan that support our strategy to achieve the state's greenhouse gas emission targets, as well as additional opportunities to achieve carbon neutrality. We continue to work with other agencies, academics, and international partners. Each of these bring expertise and authority and a diverse set of experiences that serve as assets as we advance the topic of carbon neutrality. As we explore carbon capture, sequestration, and options for utilization today, there are several underlying questions that frame the discussion. What are the biggest barriers to near-term deployment of capture technology, both from stationary sources and directly from the atmosphere? And what actions can industry and policymakers undertake to overcome these barriers? How can existing infrastructure be transitioned to process, transport, store, and monitor carbon dioxide? And what are the trade-offs between reducing fossil fuel combustion versus relying on carbon capture and sequestration for achieving our deep decarbonization goals? So now I will turn it over to my colleague, Jordan Ramalingam, to introduce our panelists.
All right, thank you, Maureen, and good afternoon, everybody. So I'm going to go ahead and introduce our 6 panelists today. The first of those is Ben Haley, who is not here physically with us, as you can see, but he is joining us remotely from New York. He is the co-founder of Evolved Energy Research, and he has unique experience developing energy systems models to support energy transformation decision-making. And he will share insights from recent modeling studies that explore net zero emissions in the US. After Ben presents, we will have Lee Beck, to my left here. He's the Senior Advisor for Advocacy and Communications with the Global CCS Institute. So Lee works closely with diverse stakeholders across North America to enhance the understanding of CCS and its potential role in future emissions reductions. and she will share perspectives, especially on policies associated with deploying CCS. To her left is Jeff Brown, who's a principal with Brown Brothers Energy and Environment, LLC. Jeff has lectured and conducted research for the Steyer Taylor Center for Energy Policy and Finance at Stanford University, that is a mouthful, and is recently associated with the University of Wyoming. And he has decades of experience in energy and infrastructure project finance, debt, capital markets, and financial commodity derivatives. Today, he will share perspectives on the potential for industrial decarbonization in California. To Jeff's left, we have Jennifer Wilcox, who is a professor at the Worcester Polytechnic Institute, and we're very honored that Jen could be here today, given that this is her second presentation of the day. She started the day out in San Francisco this morning and presented on a panel at the American Geophysical Union, and we are grateful that she made it over here in the rain. So Jen has served on National Academies of Sciences committees to assess carbon capture methods and impacts on climate, and she'll provide especially an overview on direct air capture today. And then lastly, we have two case study presentations that are highlighting two companies that are active in this space. So first, we'll have Jeff Holmes, who is the lead on regulatory engagement and public outreach for carbon engineering. Jeff has been working on direct air capture applications in both an academic capacity and in the private sector since 2008, and he will share experiences deploying the technology. And then lastly, we'll have Keith Pronsky, the president and CEO of Clean Energy Systems. Keith has 30 years of experience in the power industry and is the CEO of this company, which is deploying innovative carbon capture technology. And he will share experiences deploying a carbon negative energy renewable hydrogen project. So with that, I will go ahead and turn it over to Ben Haley. And so we'll be projecting his webcam onto the screen, and you'll be able to hear him and see him in a second. There he is. Ben, go ahead.
Hi, sorry I couldn't be here in person. I've had an awkward smile plastered on my face for the past 15 minutes because I haven't been sure I wasn't up on the webcam already. So I will jump right in here, starting on slide 2, kind of who we are and who I am. I'm the co-founder of Evolved Energy Research. We're a consulting firm that really focuses on the long-term energy system transformation consistent with some of these deep decarbonization goals, and just how deep is kind of the topic of the discussion today and what that means for carbon capture. But we're the lead developers of Energy Pathways in Rio. These are two models that we've used kind of across the United States as well as internationally to investigate these types of pathways to deep decarbonization. And I think they have, a lot to say about the issue and the opportunity of carbon capture as we go to deeper and deeper targets. Within the context of this transformation, we advise clients on policy implementation, target setting, infrastructure investments, R&D strategy, technology competitiveness, and asset valuation, which are, kind of as headings, something I will touch on as we go through this presentation. It's sort of all encompassing here as we talk about carbon capture. But going to slide 3, just to give a little bit of a history on the analysis that I'll be presenting here today. Back in 2014, we did one of the first US-wide deep decarbonization analyses. We did that for the Sustainability Development Solutions Network. We were part of an international consortium of about 20 countries that were doing deep decarbonization pathways. They represented about 80% of the emissions in the world. We were the technical team that did the U.S. reports. We did both a technical report and a policy report. And the sort of findings of that have been echoed both regionally and internationally since. Just some of the overall themes of what it means to go to sort of an 80 by 50 or a 2-degree type scenario. Going to slide 4, those themes broadly are shown here in what we call the 3 pillars of deep decarbonization. Those 3 pillars include end-use fuel switching to electric sources, so basically the process of electrification, either directly or through the production of electric fuels. The second is we have to decarbonize that electricity that serves those ultimate end uses. And third, through the process of electrification, but also in addition to that, we need to focus on energy efficiency because, these are growing systems. They require a huge amount of infrastructure. Basically, mitigating that infrastructure build is hugely important. And so anything we don't use, we don't have to supply with zero carbon sources. And that's an important thing for cost containment as well as to maintain those low emissions. So these are some of the benchmarks we saw. You about double or even more electrification, you get a greater than 90% decrease in emissions intensity of electricity generation and about a 3x drop in energy use per unit GDP. So that's what the US looks like, under the target of an 80 by 50. Going to the next slide, we, continued to push the envelope, both because that's what we do as analysts, but also because the science is becoming clearer that 80 by 50 just is not sufficient to mitigate against most of the climate risks that we're really worried about. So we undertook an analysis that was published this year called 350 ppm Pathways to the United States. The findings of that basically said that we still have it within our technical purview to reduce emissions consistent with this target as well, which is significantly deeper than an 80 by 50 target and accelerated. The costs, with technology costs coming down, we're still only in the range of about 2 to 3% of GDP. As we increase ambition in our mitigation targets, we're really aided by some of the recent technological breakthroughs over the past 5 years. So the decreased cost of renewables, the decreased cost of batteries, things like that have meant that we could increase the ambition without fundamentally changing the cost of achieving these targets. We found that delay is exceedingly costly, no surprise to anyone there. At current pace, we basically exceed our mid-century emissions budget by 2030. And there are still multiple scenarios that can achieve the scale and pace of reduction. So we aren't locked into any specific technology pathway. There are certainly consistencies between approaches, and some technologies kind of show up no matter what you do. We're going to see a lot of wind and solar. I think that's pretty much a given at this point if we achieve these targets. But there are still technological pathways that we have decision points to make on. And just to give some context, going to the next slide, what a 350 ppm scenario looks like and why we're using that. Basically, we're working off of Hanson's paper in 2017, which said that we're really going to have to decrease our CO2 emissions year on year about 6% after 2020, in addition to getting sequestration from land in order to meet the challenge of a 350 ppm, going back to 350 ppm. So if you go to the next slide, it's just showing kind of what the process is. 2 degrees going to 1.5 degrees C obviously is an increase in ambition, and 1.5 degrees C to 350 ppm is also similarly an increase in ambition. And what those really mean is that CO2 emissions have to come down. But to be honest, the larger and more impactful piece is that CO2 removal has to go up. And that is both technologically as well as land-based sequestration. So a lot of 80 by 50 analyses have maintained relatively static assessments of land sequestration and have really not dealt substantively with carbon capture as a strategy. But the increment going from a 2 degrees C down to a 350 ppm scenario is largely filled with actually deploying a lot of those strategies. So the difference, if you will, between a 2 degrees and a 350 ppm scenario is not necessarily seen in an increased ambition, say, in the electricity sector, or an increased ambition in electrification or things like that. It has a lot to do with what you start to do on the fuels and sequestration side, which I will get into as we move forward. So if we go to the next slide, we debated this. We're very judicious in our definition of pillars, but we did decide that basically it warranted another one. So the 3 pillars of deep decarbonization have really become 4, and the 4th is carbon capture. Here, what I'm showing is basically technical carbon capture. So this is not land-based sequestration. This is carbon capture on things like biorefineries or direct air capture, power plants, or things like that. And as you can see, if I'm not sure how big it is in the room, but I can narrate the scale here. In 2050, there's about 800 million metric tons of captured carbon. And that really does represent the majority of the increment between the ambition of a 2 degree C and a 350 ppm world or scenario. And so the scale of that is not minimal. It becomes a very critical piece, and so that's why we basically defined it as an additional pillar in order to achieve this sort of deeper decarbonization that we're looking at. Going to slide 9, just to orient everyone in terms of what I'll be talking about for the next few slides, definitions and nomenclature really matter in carbon capture in terms of how you're accounting for different things. So just to go down this list here, I'm broadly categorizing our carbon capture opportunities that we model as natural sequestration, which really kind of gives you the overall envelope of the target you have to hit elsewhere. So that's sequestration in enhanced land sinks like in soil and in forests, et cetera. That is obviously negative emissions when that CO2 is sequestered terrestrially. The second category here is direct air capture, and that's the technical removal of CO2 from the ambient air. If that CO2 that's been captured from the ambient air is sequestered, obviously that is also a negative emissions technology. Similarly, bioenergy, because bioenergy is basically taking CO2 from the air initially, and then once you burn it, if you capture it and sequester that is also a negative emissions technology. Fossil carbon capture is somewhat different in that if you burn fossil energy and then sequester the CO2, at 100% capture, that would be zero emissions, not negative, right? Because we're pulling CO2 out of the ground and then putting it back in the ground, and so that functionally is zero emissions. They all, as long as you're able to, capture and utilize that can, function as a mitigation opportunity. It's not to say that's somehow lesser, in our scenario analysis. It's just sort of on the ledger, how does that work out in terms of negative or zero emissions? So going to the next slide, here are some of the sectors that we see a lot of opportunity for carbon capture. And then I separate here, the difference between capturing the carbon, which is coming from all these sectors on the left here, and then what we ultimately do with it, which can be related just in terms of locationally where you can actually sequester it and how that lines up with where your biomass resources are, et cetera. But it also is somewhat separate in that the competitive dynamics of utilizing that carbon or sequestering that carbon can be unrelated basically to where that carbon came from initially. So just going through here on the carbon capture opportunities, we have heavy industry, so iron and steel, cement, petrochemicals, refineries. Separately, we have biorefining, so ethanol production, something like Fischer-Tropsch can have carbon capture associated with it. Hydrogen production, so we can capture carbon on steam reformation, on autothermal reforming. We can have a biomass-based hydrogen production process that captures carbon. We have direct air capture, and we have electricity generation, and that can be either post-combustion capture or something like an alum cycle or a net zero type power plant. So going to the next slide, we have a forthcoming analysis that is using a 350 ppm target in the U.S. similar to the report that we published. This just has some updated costs and things of that nature. And we have a broad range of scenarios. And here I'm showing the range of carbon capture from all of those different sectors based on our scenarios. So basically, in achieving, in 2050, in achieving that 350 ppm scenario, we have something on the order of 50 to 150 million metric tons of Beck's hydrogen, depending on other scenario assumptions. We have liquid fuels on the order of 150 to 350 million metric tons of captured carbon. Direct air capture goes anywhere from 0, so we have scenarios that don't use any, all the way up to 400 million metric tons. Reformation is up to 50, power generation is up to 50, and heavy industry is up to 150. And these are where we ultimately derive this carbon from is a function of a huge range of technological inputs as well as other scenario assumptions as to why we might use direct air capture or why we might, be capturing carbon from hydrogen reformation. So this isn't to say, this isn't prescriptive, but it is to give you a general scale of how much carbon we're seeing in terms of economics of capture in different sectors. And so where that captured carbon is coming from, because I think people's perception of what carbon capture is has really been focused on specifically the power sector, because that's where a lot of the original research was done, and it was competing with the renewables. Renewables have since moved ahead in terms of their cost and are really out-competing sort of base load CCS, and now we're seeing CCS kind of deployed in other sectors. But we're also seeing it in power generation, depending on renewable circumstances, whether a region has wind or solar or needs some for balancing or things of that nature. But all it is to say that it shows up across the economy, and it shows up in a really large scale. So this is not a small piece of the ultimate puzzle. And as we move past 2050, it becomes ever larger. So continuing on the discussion of that competitive landscape on slide 12, sometimes it's interesting to understand what these different carbon capture opportunities are actually competing with, because it's not always clear. So when we have hydrogen production, carbon capture and hydrogen production, that's usually competing against electrolysis. So basically, flexible electrolysis production on the grid that can also is a different way of producing hydrogen that doesn't require direct fossil inputs. Biorefining basically competes with actually not needing the fuels at all through the process of on-road electrification or through electrically derived fuels. So if we produced electrolysis and then we created a synthetic liquid fuel out of that, we might not need that amount of biofuel. Heavy industry, carbon capture in heavy industry is really competing with direct process electrification or direct use of hydrogen. Electricity generation is competing with renewables, as I noted. It's also competing with batteries, as well as fuel substitution in conventional gas power plants. So we have the option of basically capturing the combustion of gas in a power plant or substituting the fuel upstream, basically using biogas or using synthetically derived fuels in those power plants. And then finally, direct air capture is basically competing with everything and your success in almost all sectors. So, if we're not able to achieve our targets in a lot of different areas, we probably need more direct air capture at the end of the day. I don't want to say backstop because it doesn't always operate that way. It's not sort of a last resort. It actually has a competitive place in the scenarios, but it does get used quite a bit more if we're unable to achieve certain goals in things like electrification. So going on to slide 13. So I've really been discussing primarily where that captured carbon comes from in our scenarios. Where it goes to, as I said, is somewhat of a separate issue. And the competition between where it goes to is really dictated by a couple of things. One is emissions targets. The second is the cost of fossil alternatives. And the third is projected sequestration availability and cost. All of these come with huge uncertainty bands. We generally have an idea of how much we could sequester overall. At least we have an order of magnitude understanding of that. We don't really have an understanding of the rate at which we can sequester it, which is an important question. We have some sources, but there's huge uncertainty. If we're not able to sequester it, then we're going to need to utilize it. We end up utilizing that CO2 for the production in our scenarios, primarily of feedstocks as well as direct fuel use. So we create synthetic fuels and feedstocks that either go to make chemicals or plastics or fuels. And whether utilization or sequestration becomes more cost competitive really comes down to how much that fossil alternative costs and if we can use it while still maintaining our emissions budget. Going to the final or the second to last slide here, just to reemphasize, the principal activities going from these 80% reductions to something that is more akin to a net zero is really in the area of carbon capture. So it's really, particularly relevant to be having this conversation in California now. So it really does make sense that this net zero target has really precipitated interest in this area. We really need some near-term technology development, deployment, and policy support to ensure these are available at scale. It's easy to think that 2040 is really far away, but that's when we actually need to start deploying some of these things at significant scale. And it's not going to work to just sort of sit on our hands until the 2030s. We really need some policy support now to get these deployed at some scale before we can really ramp up, because there are a lot of open technical questions in this area that really do need some answering before we can, really rely on these for the emissions reductions that we're projecting. And the other thing I'll say is, initial perceptions of carbon capture, I think, focus on their competition with renewables. I think now, as I said, they really are used across the energy economy. There is some use in power generation, but carbon capture is really important in fuels, hugely important in fuels, and that needs, I think, to be the focus, or some of the focus moving forward, so that it doesn't suffer from the perception issue, which is that, we've got renewables, why do we even need to talk about this anymore? And renewables are not substitutable for carbon capture on a biorefinery, right? And so we do need to talk about this and think about ways to get these things deployed. The final slide here is just some open questions that we have, honestly, analytically as modelers, that we'd really like more clarity on. One is available sequestration injection potential. As I said, we have an idea of the reservoirs generally. We don't really have a good idea about how fast we can get CO2 into the ground, and so basically rate constraints on that. Public acceptance of CO2 pipelines is just going to be something that we need to manage moving forward. If we're not able to build as many pipelines, it's possible that we, tend more heavily towards utilization, because it's possible to co-locate some of those facilities and avoid some of that pipeline infrastructure. We need to have, an understanding of technology demonstration timelines. When can we kind of get these out in the field so we have some confidence moving forward that we can rely on them in the late 2030s and 2040s at significant scale. Emissions accounting, I previewed that at the top, but it's much more complicated than that. And we need to have a pretty rigorous protocol for understanding how these emissions are accounted for and credited, so that basically money can flow to these types of technologies commensurate with their impact on reducing our emissions. And then just the ultimate competitive breakdown in utilization versus sequestration. As I said, that can diverge along a variety of different inputs. And some of that is just we're going to have to see how one goes versus the other. But it's important to understand that they both exist as options. And so where you can't sequester, you're still able to utilize. And so we still need some focus on carbon capture even in that context. So I will stop there.
Great. Thank you, Ben. So we're going to go ahead and take questions after all the presentations have gone.
Great.
In the lights. Yeah, we'll see if we can do that. So my next presentation is from Lee. And Lee, let's get your presentation pulled up, and you are good to go.
Perfect. Thank you so much. My name is Lee Beck. I'm a senior advisor at the Global CCS Institute. We're an international think tank backed by governments and companies. I'm in our Washington office, and we're in 7 countries right now, and our mission is to accelerate the deployment of carbon capture and storage within an energy transition that leads to net zero emissions. I just wanted to thank CARB for hosting this workshop today, which we think is very, very timely, because I think with increasing climate ambition, the role of carbon capture and storage has been confirmed, both for reducing emissions for reducing the flow of emissions from existing infrastructure, as well as capturing or reducing the stock of CO2 from the atmosphere. I also want to emphasize that I think it's become very, very clear from the Intergovernmental Panel on Climate Change and other sources that climate action is no longer about pitting technologies against each other, but really at looking at it all of the above approach. So CCS's role in climate action is really to complement other sources of clean energy and other decarbonization strategies. So before I go into the policy discussion that I promised to deliver today, I just wanted to give a quick update on the global status of CCS. The Institute releases its flagship report every year at the Conference of the Parties, and so we've done so just this Monday. And there are a couple of trends which we think are very positive. For one, there are now 51 projects globally, 19 in operations, 4 under construction, and 28 in various stages of development. In the US, we're hosting 24. 10 of those are operating right now, capturing about 25 million tons of CO2 every year. These projects stretch 11 industries, and you can see them on the left, really highlighting the versatility of CCS and its ability to deliver emissions reductions in the transportation industry and electricity sector. And thanks to policy support, in particular in the United States, and we'll get to that in a second, the facilities pipeline is up 37% since 2017. We are also witnessing the next wave of projects being planned as hubs and clusters. So we're looking at large area sources, taking advantage of industrial and power plants sources of emissions being co-located, sharing infrastructure, and as such reducing costs and risk. And as such, I am going to talk about, so the question now is, we've seen a scenario from an international perspective. The International Energy Agency expects that we need about 2,000 facilities operating by 2040. And that implies a scale up of 100 or a 100-fold scale up. So the question is really, how can we get there? And with 70% of investment in the energy transition, either directly by governments or as a direct result of government policy, we're looking to governments around the world to help us deploy CCS at scale. So what we did at the Institute earlier this year is we analyzed the facilities that are currently under construction and in operation, and identified the mechanisms that made them happen. And what we found is there's really a policy framework that can be thought of. So the first one is all but one of these facilities were built in an environment that had some kind of value on carbon, reflecting the externalities of pollution. And this can be a carbon tax, like, say, in Norway, which delivered, where a carbon tax of $45 delivered 2 facilities, but it can also be an emissions tax, a tax credit for sequestration, like we have in the United States. The second one is, what we found is that most of these facilities had little to no classical debt financing from financial markets, but relied on grant. In the US, even 60% grants. So we're seeing that CCS, like other technologies, is a proven technology, but it hasn't been deployed widely, and as such is facing this technology valley of death, which we're hoping to overcome, and where we need really government and policy support to overcome and lead to large-scale deployment. Finally, all of these facilities also had access to infrastructure, highlighting and underlining the important role of CO2 infrastructure, CO2 pipelines as an enabler for CCS deployment, as well as well-understood geologic storage. Now, in our view, the US government has done more than any other government in the world to commercialize CCS, but also to understand its storage, which is in abundance and can hold multiple hundreds of years of emissions. So let's talk a little bit about the policies that are in existence. So Maureen already talked a little bit about the low carbon fuel standard CCS protocol. I think we're all familiar with the LCFS, which seeks to reduce the emissions intensity of fuels in California by 20% by 2030. And so the CCS protocol, which came into effect earlier this year, is applicable on projects, CCS projects, or allows CCS projects that can reduce the life cycle emissions of fuels sold in California to generate credits, which are currently trading at roughly $195 a ton. So, for example, if you're producing oil and using a dedicated power plant, and you're equipping that one with CCS, that would qualify because it reduces the life cycle emissions of the fuel produced. The same holds for refineries and, for example, biofuels. what we think unprecedented move, and also really recognizing that climate change is a transnational problem and that negative emissions on the road to net zero ambition are needed, the protocol also incentivizes direct air capture facilities anywhere in the world, recognizing and emphasizing that we need to commercialize this technology now so it can be ready when it really makes significant contributions to emissions reductions in the models in the near future. So as such, the LCFS is a really innovative policy, but obviously it's limited to transportation. Then in the last year, Congress on the federal level reformed and expanded the 45Q tax credit, which from the Institute's perspective is the most progressive CCS-specific incentive globally. It will eventually, by 2026, provide $35 a ton for CO2 stored via enhancer recovery and $50 a ton for CO2 stored via geologic storage. However, projects have to be in the ground, or projects have to have commenced construction in the beginning of 2024, which really shows that we have really a short window of time to capitalize on this opportunity. The credit has no limit to what it can be applied to. It's really about the storage part and storing the CO2, and it's also a very provides a strong business case for CCS on its own, but even stronger because it can be combined with a low carbon fuel standard. And we've already seen project announcements, which we'll talk about in a minute. There are some differences between claiming 45Q and claiming the LCFS. I won't go into detail to all of them, and we'll submit our report in lieu. But obviously, key difference that I highlighted is LCFS is direct air capture and transportation. 45Q and is to all industries that capture and store the CO2. The lifetime of how long it can be claimed is different. So for the LCFS, it's for the duration of injection. 45Q is for 12 years. And as I said, I think the key difference is that there's a deadline for when projects have to have steel in the ground. However, the 45Q tax credit also hasn't been formally implemented yet by the IRS. So while we've seen first projects being announced, we're expecting more projects to be announced once it's actually clear how to claim the credit and what kind of projects actually qualify. So earlier I talked about the fact that that policy confidence, or that we're looking to governments to help us and help carbon capture and storage really overcome this technology valley of death. And so I just wanted to highlight that policy confidence can lead to projects. So I think 2 months ago or a month ago, the Global CCS Institute updated its global database, and we added 10 projects, 8 of which were in the US. And all of them were driven by sustained government support, as well as 45Q, or a combination of 45Q and LCFS. And so I just wanted to highlight that these incentives have begun driving this next wave of carbon capture and storage facilities. So for example, in I think May this year, and we'll hear about this probably more later, the first large-scale direct air capture facility was mentioned and was announced, and it mentions the LCFS and 45Q as a cornerstone of their economics. We're seeing ethanol facilities being announced and being retrofitted. We're also seeing industrial carbon capture, as well as this move to large-scale hubs and clusters. So 6 of the projects we added are as a combined result also of the Carbon Safe Initiative by DOE, which aims to develop sites for storage of 50 million tons per year and more. So we're really seeing that this trend of new technologies, diverse technologies, new applications, but also scale is taking off. We're also seeing new business models. So for example, there was an intention for an offtake agreement of CO2 signed, which also cited LCFS and 45Q. So I think there's these incentives are really driving new projects and new innovative projects. So as such, I think earlier I talked about the fact that that the International Energy Agency argues that we need about 2,000 facilities operating by 2040 to meet our climate goals. And I also want to emphasize that the IPCC made it very clear that the sooner we can reduce emissions, the better our chance at fending off the worst case climate scenario. And as such, near-term emissions reductions and near-term deployment of CCS are very crucial. And this also overlaps with this very short window of time that we have for 45Q for projects to capitalize on 45Q. So I think it's really important to recognize this urgency and think about what can we do to really capitalize on this CCS-specific incentive. So to go back to the policy framework that I introduced in the beginning, from a value on carbon perspective, I think attaching the CCS protocol to the cap and trade market is certainly one option that would allow industrial carbon capture and storage to have an additional value on carbons. California is the second largest cement producing state in the country. Only the Norwegians are currently working on a large-scale cement CCS facility. So I think there's a lot of innovation that we can drive. On the demand side, a lot of policies could still be developed, innovative policies, how we can incentivize the procurement of low-carbon products whose life cycle emissions have been reduced with CCS. I know California has legislation that is already applicable and that actually globally has raised a lot of interest. Furthermore, I think what's also really important is to understand is how can we create pathways for CCS to play a role in the decarbonization of the electricity sector, particularly natural gas. Natural gas was the fastest growing fuel globally in 2018, and the average age of a natural gas plant globally is 19 years. So to prevent infrastructure emissions lock-ins, we really have to deliver carbon capture and storage on natural gas plants. And I think the Energy Futures Initiative in a report earlier this year also highlighted that in California, it could actually help or deliver the largest emissions reductions with regards to your 2030 goals. And then finally, to talk about the two other parts of the framework, investment support mechanisms, helping CCS overcome this uncertainties and reducing risk. So finding ways to have additional financial incentives and additional incentives that can unlock investment, including grants, investment tax credits, concessional loans. I think there's a variety of policy options, but really understanding, okay, how can we help bring in further investors into these projects and also enable affordable financing, because the cost of debt is really very important to the sanction of these projects. And then I think capitalizing on this trend of the new wave of projects being hubs and clusters, how can government help to build out key infrastructure that can unlock further emissions reductions? So I want to cite the Alberta Carbon Trunk Line in Canada, which we expect to be the next two projects coming online. The 240-kilometer CO2 pipeline was built with grants from both the federal and the government of Alberta, and it's going to go online with just 1.5 million tons of CO2 flowing through it, but its capacity will be more than 10 times as much, giving other projects the ability to tap into the pipeline, which is already built, and as such, reducing cost, reducing risk, and allowing each company to focus on their core competency. And so I think that we think that this is really a key role for governments, showing that they're also invested and committed to the long-term decarbonization and the long-term decarbonization through CCS. So I think I will stop here. Happy to answer any questions and giving it over to you.
All right, thank you, Lee. So next we have Jeff Brown.
How about now? Yeah. All right. So first, I wanted to actually thank Lee for what she said about we're talking not do we have the technology to do carbon capture, but are we deploying it? And since I've been teaching for the last 5 years, I like waking people up. So here's my contest for you all. The students, I typically buy them a bottle of scotch, but I don't know if I'm allowed to do that here. So who can guess what year the prime carbon capture technology is, that we now use, was invented? Anybody other than George and Deepika? Okay, so what year? Okay, this is not new technology. That's my hint. So what year was it patented? Amine solvent technology for taking CO2, scrubbing it out of gases. Ooh, who said 1921? Close. This is 1930. Okay, so we're not talking new stuff. Part two, the U.S. has injected, say, 1.5 billion tons of CO2 underground in the last 40 years in the oil industry and has about 5,000 miles of CO2 pipelines. So here's another numbers question. How many people have been killed by CO2 leaking out of these pipelines or at the oil fields? 0. Okay, good. All right, so with that said, going on to the first slide. So the key topics, and pardon me, I've given my eyes in the service of the environment, so I have to have my giant screen so I can see. Maybe I'm just getting old. So key points. Who are the major industrial emitters, and what's their relative size versus the power sector? What are the likely costs of capture in the subset of industrial emissions that are most practical to capture? How do the industrial sector emitters compare to the cost in power sector? So is capture costs in industry a lot higher or a lot lower than in power? What do existing reports say on the topic? And then wrapping up with how do CARB rules and changes to those rules, both on cap and trade and LCFS, help or hurt the prospects for industrial capture? And what are some of the other regulatory and permitting issues that need some special attention? So, and some of this stuff, I'm glad Maureen and Jordan invited me here because I hadn't reviewed this stuff for a while. So here's of the big emitters in California, and this is above 500,000 metric tons a year. That is relevant because if you're trying to do carbon capture, in general, scale is your friend, right? It takes a long time to permit, and you have to set them up, and you have to have pipelines. You like scale. So of the big emitters, on the top, I put refiners. So basically, the Bay Area is about 45% of refining emissions, and SoCal is the other, about 55%. Of the big emitters, above 500,000 tons a year, refining in the Bay Area and LA is half, 52%. Cement, interestingly, is another 10% of all the emissions. Power plants are about 36%, and all the others above 500K are about 1%. So really, you have power, refining, and cement, and you're there. We're not supposed to talk about power today, so I'm going to talk about primarily refining and cement. So now, focusing on the industrial emissions, it's a pretty easy little pie chart, and I color-coded it, so black is refiners, and that is 35 million metric tons a year. That's including hydrogen, and kind of sneakily, it also, most of the time, includes power plants that are built into oil refineries. So if you think, for instance, that there aren't power plants burning coal in California, you're wrong, because there's power plants inside refineries that are burning petroleum coke, which is actually nastier than coal. But they're behind the fence, so they don't really show up anywhere as power plant numbers. 7 cement plants are about 16%, and then everybody else almost doesn't matter. Here's the big refineries, and again, you can just see I colored in purple, are the Northern California refineries, almost all in Contra Costa County and one in Solano, and then a whole bunch in LA County. And so what that means is that 35 million tons is really split among two spots, and you have two logistical challenges to take any captured CO2 away. You basically need a pipe out of the LA basin and a pipe out of the San Fran Bay area. It really helps if you're talking, now I'm going to talk about refineries first, because it's a pretty interesting thing. There's a big misconception that, well, how much would it cost to add CO2 to refining? Or how much would it cost to add CO2 to a steel mill? That's a really bad way to ask the question, because each one of those things is like its own industrial city, and it has 25 or 40 or 50 different vent stacks, which we used to call smokestacks when we were kids, and they have continuous emissions monitoring systems on them. There's only a few of those that are worth bothering with. So I just wanted to give you one example, and this is the way we all have to look at the problem. We're not looking to capture all emissions initially, because we have an urgent problem. We're looking at capturing the big cheap ones initially just to get going. This is a pollution control problem. So here you go, one example. Chevron El Segundo in LA County, and there's a nearby Air Liquide hydrogen plant. Almost all refineries have to have a hydrogen plant because hydrogen kind of acts like, call it like paint thinner in paint. It thins out the ultimate product to make it more like gasoline, less like asphalt. So sometimes it's inside the fence, the hydrogen, sometimes you buy it from an external provider. Between the two, there's about 4 million tons a year emitted from this refinery complex. My estimate is, I'm going on the left-hand side of the slide, that you could capture about 45% of that at pretty reasonable costs. By reasonable, I mean somewhere in the 40 to 60 buck a ton cost range. But it gets divided up in funny ways. So the EPA will show stationary combustion, which kind of sounds like water heaters, but in reality, there's 22 different vent stacks. Most of them are tiny, but there's one 800,000 metric tons a year, which is a power plant inside the fence. It makes power and also steam. That is an awesome candidate for carbon capture. Why? Because a power plant that's captive inside an oil refinery runs all the time. It doesn't turn on and off with wind and solar. It's their own little power plant, and I'll discuss that. But you can imagine it's a lot more economical to capture carbon from a power plant that runs every hour than to capture carbon from a power plant that sometimes it's off, sometimes it's half speed, sometimes it's full speed. Hydrogen, between Chevron and Air Liquide, that's another 1.1 million tons. And then inside the refining process, again, so if you look on an EPA report, they'll say refining, well, that's 0.53 million tons a year, 6 different stacks. But there's one big one, which is called the regenerator for the fluidized catalytic converter. It's basically some things that look like little pieces of metal sand. Pet coke sticks to them as you're trying to make the fuel mix nicer, and then you burn the pet coke back off and get steam. So the point is that here we have, in the aggregate, about 30 different stacks, but really 4 are relevant. One power plant, and one phone that should be turned off. So you've got, 30 different stacks. You've got 4 that are relevant. A power plant, 2 hydrogen plants, and 1 catalyst regenerator. So that's kind of the way you look at the cost of carbon capture. Next, what does it cost? I'm sorry. Hey, thanks, Jen. There we go. Yeah. And I just put in red the things that are important. Generally, the higher your concentration, the better and cheaper. So typically, and I've spent about the last year doing cost work, but hydrogen plants, cement, and the catalytic crackers are all kind of in the 40 to 60 buck range. because they're somewhere depending between 16 and 50% concentration. But just to say, take cement, which is typically about 20%. Well, that's good because that's 500 times higher than atmospheric concentration. So if you want to get good at direct air capture later, it kind of helps to warm up catching carbon molecules when there's 500 times more of them, and work your way up to where there's not very many. What I also wanted to mention, I just did, but lower right, when I normally am looking at a natural gas power plant, well, I'd say I run the numbers at an 85% capacity factor. There it's 65 or 75 bucks a ton. But if I'm only running it at 50%, because I'm whipping it up and down, it can be 105 to 115 bucks a ton, because I've got fixed costs and I'm basically not catching very much carbon to spread over those fixed costs, right? So in general, since, for instance, most of the gas plants in the power sector are gonna be running, unless we change the way we do it, at a low capacity factor, I just wanted to emphasize that power plants that run all the time inside the fence are actually, they're treated as industrial, but they're a very good way to do power sector carbon capture. I'm going to quickly just say the Energy Futures Initiative did a study on California. Most of the people here are familiar with it, and I'm not familiar with running my slides properly. Thanks, sorry, I just can't see the ones on the tiny monitor. But so EFI said, you can't really see these numbers, but there's about 30, according to them, about 30 million of refining sector emissions, and they suggested that you could probably grab about a third of those. And that seems about right to me. On cement, they said there was about 7 million of emissions, and you could grab about 1.4 of that. I think probably the number is probably closer to 3.5. You could grab about half of those you could grab effectively, but it could be as much as 6. Just wrapping up in terms of what the Air Resources Board has been doing. The refinery and hydrogen, right? So that was the big black, most of the big emissions. Well, there is a big opportunity. CARB did something really great in 2018. The LCFS changes to implement the carbon capture protocol. What they did was they took a cap that used to exist on the amount of refinery investment to capture carbon that could be used to offset your carbon intensity deficit. It used to be, say you were a refinery and you had to buy 1 million allowances a year. If you captured 1 million tons a year, you actually would only be able to use 20% of that. So you could use 200,000 of the 1 million tons you captured to fix your 1 million ton deficit, but that's it. So clearly that wasn't very attractive. That was fixed, and that is a really good thing. But if you take the second offender cement, it's not connected, obviously, other than you make roads out of it with a liquid fuel life cycle. And so the only money that a carbon capture plant attached to cement in California can get is to avoid paying your usual cap and trade allowance fee. And so those aren't very high, right? Those have been going up. There's a minimum floor, goes up with inflation. The floor is now 1668. The weighted average auctions this year have been 1677. So it's bumping along at the floor. Again, so you've got the disparity of 200 bucks if you're in the liquid fuel life cycle and kind of 16 if you're not. Also, there's no cap and trade. As I understand now, there's still no cap and trade. I'm sorry, no sequestration protocol relating to cap and trade. So even if you caught it, you couldn't really get the 17 bucks yet. So cement, I think we have to work on a little bit harder. Key issues we can talk about later, but somehow we do need CO2 pipeline if we want to do this out of the Bay Area in the LA Basin. It's important to know this is sounds, what's Class 6 primacy? Those are passive sequestration wells. A number of states are trying to get primacy, which means the state can issue the permits instead of waiting for the feds. That's important because right now EPA only has 2 guys working on these permitting, and supposedly they're both retiring. So it would be good to have the state, which is well-funded and smart, doing this. I'm going to say just one thing. There's a perception that carbon capture may not be great for environmental justice. Well, if you think about it, inside an oil refinery, if you're basically burning pet coke in connection with your catalytic cracking unit, that's like having your own little backyard coal power plant, and you have to clean that exhaust up a lot if you want to do carbon capture. And then last, a thing that has come up in discussions is there's no floor on LCFS prices. So it's 200 now, but you can't tell what's the minimum. It's a different program than cap and trade, but at least cap and trade, you've got an idea that there is a minimum floor that you can count on if you're running your debt, your affordability analysis for debt, as Lee talked about. It's handy to know what's the rock bottom rather than zero. So, 2 questions later, but I hope that gave you a little grounding in what's around.
Great, thank you, Jeff. And let's move to Jennifer's presentation.
Okay, thanks for having me here. Giving an overview talk on direct air capture, really. So in that framing, I want to think about just making sure that we're all on the same page. Direct air capture is not a silver bullet in terms of negative emissions technologies. It's really one of a portfolio of negative emissions opportunities. And also to follow up on what's already been said a little bit, is that we also have to be careful to not treat some of these negative emissions technologies in a vacuum. Like, in order to actually be negative, they have to couple to geologic storage, like direct air capture. So what is direct air capture? Looking at just this as an example, there are some pros and there's some cons associated with it. It's really looking at using chemicals to directly separate CO2 from the atmosphere. Pros is it has the potential to be a negative emissions technology. It's also a method for dealing with difficult to avoid emissions, so sectors that are really difficult to decarbonize, as Jeff already talked about, cement manufacturing, refineries, iron and steel, but also the transportation sector. And another benefit is it doesn't require arable land, so it doesn't have the same competition for food that biofuels have. Cons, so here I have just a couple, but looking at the energy inputs, we'll talk a little bit about this in the next slide, but it's significant. So to think about taking CO2 out of the air, it's a difficult problem energetically, because CO2 is so dilute in the atmosphere. So it's not just about designing a direct air capture plant, but you also, again, have to think about the system, and it's about designing a power plant to couple to the DAC plant. And in the land area to do this is not insignificant, and I'll give some examples of that in a bit. I think the overarching message here, too, is that direct air capture should not be seen as a replacement for mitigation. It will always be easier to capture CO2 from point sources. This next plot gives you an idea of that. So what I'm plotting here is the combined first and second laws of thermodynamics to show what the minimum work is for a given separation process. So in order to get an estimate, what you really need to know is what's the initial CO2 concentration that you're starting with? How much of that CO2 do you want to capture out of your gas mixture? So what percentage of CO2 capture? And finally, what's the purity, the end purity of the CO2? Mostly for carbon capture and storage, we talk about high purity CO2, because typically you have to move it, whether it's in a truck or a pipeline. So you need it to be able to go in a condensed form easily upon compression. So we're looking at 99% plus purity as an end. So what I'm showing here is just a comparison of some more concentrated streams. Jeff talked about some of the industrial streams too, and in some cases you have certain streams or exhausts out of an industrial facility that might be higher in concentration than some of these that we're even seeing here. But for instance, in the exhaust stream of a coal-fired power plant, it's on the order of about 300 times more concentrated than CO2 in the atmosphere. And what that translates to is, in order to capture the same amount of CO2 from air as you would from that kind of a unit, you have to actually have a contactor that is 300 times greater in surface area. And what that does is translate directly into increased capital costs for the DAC plant versus the point source capture plant for the equivalent carbon capture. In terms of energy, again, this is really a minimum energy perspective. So of course, in a real process, you have to break it down into all of the different aspects, which I'll talk about in a bit. But if you think about, for instance, capturing CO2 with a chemical, you also have to think about using that chemical over and over again. So what you see in direct air capture is that it's in the technologies that are kind of driving the field today, they're very thermally driven. And so you capture the CO2 with a chemical, and then you need heat in order to drive the CO2 back off and use the chemical over and over again. And so in that process, there are efficiencies associated with it. And so a real system will have efficiencies, but the minimum work is as low as you could possibly go. And even in that scenario that we're seeing here in this plot, for more concentrated sources can be 3 times or greater, or for more dilute sources like direct air capture is 3 times or greater the energy compared to the more concentrated sources. This is an example of an actual successful carbon capture plant that we have. It's Petronova, and I knew the answer to Jeff's question because I have it right here. So the first patent filed by Bottoms in 1930. So we've been doing this for a very long time. We understand the technology. We understand what goes into this tall, thin tower that I'm showing here. And originally, this was actually done because we wanted to produce CO2 for beverages, so for food and beverage industries. It had to be extremely high purity CO2. And so we used amine scrubbing to do that. And so that's what's being done at Petronova today. And so this plant is capable of capturing 1.4 million tons of CO2 per year, and ultimately is geologically sequestered through enhanced oil recovery. And so that's an example of point source capture. And so if you look at the cartoon on the left, and you see these different, if you're not a chemical engineer, this may not be familiar to you, but you see these different horizontal lines that run up the tower. So the idea is that the exhaust stream is bubbled up through this tower, so it enters through the bottom. The tower is filled with packing material, and then you pump a solvent that has the chemical in it, amines in this case, that essentially is pumped down the packing material. And the goal is that you want to make intimate contact between your carbon dioxide in your gas and the chemical in the liquid solvent. And so what happens is as you move up this column, your gas is becoming cleaner and cleaner in CO2. And as you move down the column, the solvent is becoming more and more concentrated in CO2. And so, of course, you have to take that solvent, heat it up to regenerate it in a separate unit. But the idea, too, here is that how much CO2 do you want to capture? Could you capture all of it? If you wanted to capture all of it, you would have to have an infinitely tall tower. Because every one of these stages, every one of those horizontal bars, as you move up, you get cleaner and cleaner of CO2. More CO2 is depleted. But it would be infinite costs to do that, so we don't do that. So it's an optimization. And a lot of targets today are centered on 90% capture, but they can be higher than that. But in terms of direct air capture, it actually becomes a variable that's very important to minimize costs. And so this is an example of what a contactor would look like for direct air capture. Very different from what I just showed. So rather than tall and thin, now you see something that has a huge contact surface area, and you see something that's shallow in depth into the wall. And the reason for that is because you look at that and you think, well, why not go deeper? Don't we want to capture more CO2? But the amount of CO2 you capture is an optimizable parameter to minimize costs. And so you make it shallow because you don't want to spend too much fan power to actually push the gas through. And that's called pressure drop. So the deeper the bed, the greater the pressure drop, which translates to greater power to overcome the pressure drop. And so what you can see here is really just a system that's been optimized such that Ultimately, in the end, the percent of CO2 that's captured for direct air capture plants is ranging between, say, 60 to 75%. And that's, again, to minimize the operating expenses of the fan power. Now the question becomes, well, what's going inside this contactor? There's two leading technologies that I talked about today. There's a lot of other technologies that are exciting, but just not at the same technological readiness level as the ones I'll describe briefly. And I won't go into too much detail on solvents because that's Jeff right over here, and he's right here. And we'll talk about carbon engineering. But that is one of the approaches. And so the top is looking at, that's a structured packing material. That one happens to be made of metal. And that structured packing material goes inside the contactor, and that's what you're pumping the solvent down through. The bottom right, I'll talk a little bit more about this. This is a solid sorbent-based technology, and so the companies that you might have heard about in the news are Global Thermostat, Climeworks. This is the type of technology that they use. And this is, if you've ever taken apart your catalytic converter in your automobile, it looks just like this, in fact. And so it's a honeycomb structure, and you see that the size of those, the channels are on the order of millimeters, again, to minimize pressure drop. You want that air to move through easily. The other aspect about this is the chemicals. So the chemicals are embedded in micro-mesoporous materials. Those are very high surface area. The materials that they're using today, actually per gram, have the kind of surface areas greater than 2 to 3 football fields in just a single gram of material, much higher than the activated carbons that we're used to. So they're very advanced in that way. And so the idea is that those materials would ultimately go into a unit. And the interesting part about the solid sorbent case, too, is that you can both capture CO2 and regenerate CO2 in the same unit. So it's kind of fewer units in the end than looking at, say, a solvent-based approach where that liquid has to be recycled in a separate regeneration tower. So this is something I alluded to before. So in order to think about direct air capture, you also have to think about, well, what's the energy resource that you're going to couple to it? If you're going to all this effort to remove CO2 from air, you really want to make sure you're fully aware of what's the carbon intensity of all the flows going into the system, including your energy choice. And what it boils down to here is, depending on that energy choice, you actually might require a power plant on the order of 300 to 500 megawatts just to remove 1 million tons of CO2 from air. This is, so I had the honor of being part of a committee. The National Academy of Sciences put out a report on negative emissions technologies, and this was released in January 2019. And Chapter 5, in particular, in that study is focused on direct air capture. We looked at both scenarios of solvent-based separations for DAC and also solid sorbents. And this is just, well, I'll also back up and say the charge of our committee was to establish a research agenda for negative emissions and to try and put forward where should dollars go in terms of research and development, and what might these projects look like. And for direct air capture, what we concluded is that the technology is ready today. It's ready for deployment. But what we need to be able to understand is, how can we get the costs down? So we need to deploy, and then we need to learn by doing so that we can realize lower costs. And in the literature, you see a range of costs for direct air capture, some as low as $100 per ton, and some as high as $600 or a little higher than that dollars per ton. And so what we aim to do in Chapter 5 of this report, if you want more details, you can take a look, the reference is below. But what we aim to do is really look at, well, what are ranges associated with each of these technologies? And what I'm showing here are averages. And so in the liquid solvent-based case, what we wanted to think about, this is capital costs only in this plot that I'm showing. We show operating in the report, but the idea here is, what are the big ticket items that are making it difficult maybe to build one of these plants? And is there a way that we can think about investing in research such that we can bring the costs down of those big ticket items? And so in the solvent-based case, what we looked at is, we looked at a range of different calcining technologies. We went from an oxy-fired calciner, but the oxy-fired calciner, this is technology that's used today in the glass-making industry. And why? It doesn't have to do with CO2, it has to do with NOx and SOx. And so when we had regulations associated with NOx and SOx reductions, there were industrial facilities that looked at trying to establish technologies that would help to prevent the emissions of those precursors to acid rain. And so oxy-fired kiln technology was one of them. And so the oxy-fired kiln technology, there's a lot of different things within that. You can have a fluidized bed kiln, which means you have great heat transfer to the particles, but maybe that's more expensive than a rotary kiln, which is what's used in the cement manufacturing industry. And so what we're showing here in that blue bar is really an average across all these different technologies, because it's not clear yet what is going to be the best for this. When you look at, and I'm sure Jeff's going to mention this, but when you look at Carbon Engineering and their project that's cited for Texas, it looks like a scale of 1 million tons of CO2 per year. That's a large scale. And when you look at the kiln technology associated with the glass industry and the cement industry, it's not as large of a scale. So it's a question about, can we try and figure out how to make this equipment at a larger scale? The other piece is the contactor, and that was another range. When I showed the slide that had the bottoms patent from 1930, that was based on metal packing. And the other aspect is there could be newer technologies, not based on metal, but based on plastic packing that have lower pressure drops and cheaper to make. And so that leads you to a range of costs. The thing we know how to do today might be expensive, but can we invest R&D in order to realize the lower costs? In terms of the solid sorbents, you can see that big orange block. 80% of the capital associated with the solid sorbent-based technology has to do with those micro and mesoporous materials. We're not very good at scaling them up today, and they're dominating the costs. And so that's another really interesting area to look into for research and development, is trying to figure out how to make this stuff at a larger scale. Sure, that's dollars per ton.
Per year of capacity.
So per year of capacity, yeah. And then the other aspect is in terms of research and development, we wanted to kind of look historically and say, well, when did we look at investing in research in science previously? And so I took as an example the Apollo program. And so in 1966, the US invested about 0.5% of GDP in getting us to the moon and safely back to Earth. And today that looks to be about 100 billion tons. And so knowing that direct air capture is really just one aspect of a whole suite of negative emissions options, we said, just suppose that we invested 20% of that in direct air capture. And what would that look like? So that would be a $20 billion investment. And then also let's suppose that we can get the costs down for direct air capture as low as $100 per ton. So if we could do that, what would it mean? It would mean building about 200 of these plants, each capable of removing 1 million tons of CO2 per year. And so what we're doing, we're working on a study now where we're actually looking at coupling the energy plant or the power plant with the direct air capture plants. And we have about 9 different scenarios that we're looking at. And so here is just one example. This is as we outlined in the National Academy of Sciences report, and I think what's conventionally thought with the solvents today is thinking about using natural gas with carbon capture. And in that approach, you do have to be careful, and don't worry about all the boxes. That's just the complexity of the carbon engineering process, and I'm not getting into that. But what I want to talk about is the coupling of energy to the DAC plant. One thing that we do have to be careful about with this scenario is what are the embodied emissions associated with the recovery of natural gas? It's not just about CO2, it's also about the methane leakage associated with that. And so we have to be really responsible in thinking about the ultimate impact on climate when we couple energy resources with the direct air capture plant and try to have the highest impact as possible. So in our Academy of Science report and in the current study that we're working on, I was asked to specifically look at, can we envision a fossil fuel-free coupling? And so we did. And it's a little complicated, and I'm not even sure it's the right answer. I don't know what the right answer is. That's why we looked at a lot of different scenarios. But here, what we're looking at is assuming that we had a different type of kiln technology. I talked about oxy-fired, but suppose that we could have a hydrogen-fired kiln, so that when you burn the hydrogen, you're producing water vapor. There's also, suppose you have an electric-fired kiln. So there's a lot of different options by which you could imagine heating to regenerate in this cycle. And so we specifically, in this case, looked at using photovoltaics to split water and ultimately use that hydrogen for a hydrogen-fired kiln. Now, A little bit of the issue with this is that some of these direct air capture technologies, these are meant to run 24/7 or 90% of the time. And we know that the capacity factor of solar might only be 40%. And so being able to try and match those capacity factors of renewables to some of these plants that are meant to just run longer than that is difficult. And so what we ended up having to do is oversize and, the photovoltaics and also have battery storage. And that's going to make an impact on the land requirement. And so to just give you a comparison, on the left-hand side, when we look at capturing 200 million tons of CO2 from the air using natural gas, it's about 1/6 the land area of San Francisco. And these are just rough estimates. This is still a work in progress, so you don't need to cite it or critique it quite yet, but it's a rough estimate. But then on the other side, you can see, suppose that we were to use photovoltaics and also hydrogen in the heating technology. It's about 1/10 the land area of California. So it's pretty significant, and it really goes to show that the energy density of fossil. These are very energy-intensive plants that we're building, and the amount of solar that you actually need to carry this out is not insignificant and shouldn't be underestimated. So in the last couple of slides, I just want to share with you some takeaways that I've learned in this field. And this is based upon work that I've just really done in the last couple of years. And on the first one is, so first I'll back up and also say that the two leading technologies that I've talked about, although there's others, and it's pretty exciting, there's a lot of work going on right now in this field, I call them low and high temperatures because the solid sorbents only require 100 degrees C roughly, and in some cases even lower, in order to regenerate their materials. The liquid solvents, as I know today, it's about 900 degrees C to regenerate their materials. So they're very different approaches, and both have their positive and negatives. So going through the low temperature first, we started a study working on that because it's just easier to find low carbon, low cost thermal energy available for that temperature regime, 100 degrees C. It's not that difficult, actually. And so what we did is we did a study where we focused on geothermal. We looked at all kinds of opportunities in Nevada and California where there's geothermal working fluids on that order. And then we also looked at a lot of industrial facilities. And there's public data out there on industrial facilities like cement plants, refineries, iron and steel plants. Again, a difficult sector to decarbonize. And there's a lot of waste heat. And some of it can be as low or as high as 100 degrees C. And so what we did is we looked at all of those opportunities and coupling it to solid sorbents. And when we added them all up, first I'll say that by coupling to these kinds of opportunities, it does keep your direct air capture plant pretty small. And so the sizing of the direct air capture plants that we could see were all on the order of, hundreds to 1,000 kilotons, like all pretty small. And I'll just mention that the company today, Climeworks, has about 14 sites globally. And if you add up all of what they're doing, it is less than 5 kilotons. So to say that maybe we could find these opportunities and they're on the order of kilotons is still very interesting, and it's still a step forward in helping us to scale to this next level that we need to get to. But that is what we saw. It's kind of keeping them small. Collectively, when you add it all up, it's on the order of millions of tons, but not much more than, say, 10 millions of tons. And that's also all very important in consideration of 45Q, which has lower limits, in terms of actually being able to qualify. And so maybe that would have to be changed a little bit in order for some of these smaller facilities to qualify. The other aspect is that when you look at those energies, that means that you have to build the direct air capture plants where that energy is. You have to have close coupling between the energy resource and the plant itself. And then you have to ask the question, well, what are you doing with the CO2 once you separate it? And what we'd like to do with the CO2 is put it back in the ground where it ultimately came from, so that it's permanent removal. So then it becomes a mapping exercise, because you have to say, okay, well, where's my low carbon heat? And then where is my sequestration opportunities? Where are all of those sedimentary basins where I can inject the CO2 in? because you don't want to have to, if you don't have to invest in the infrastructure for transportation, you shouldn't, because it can become cost prohibitive. And so it's really a mapping exercises in trying to figure out where those overlaps are. I think a significant benefit of the carbon engineering approach is that in that case, the economies of scale are working for them, and so they're building plants that are on the order of millions of tons of CO2 per year. And that means that you could build that plant directly above where the sedimentary basin is. But you still have to ask the question of what is the power plant that's going to couple to it. And I think in that case, you just have to kind of explore what those options are. I want to also say, and I kind of actually combined these last two slides, but so I've already talked about that top bit, but at the bottom, I want to also mention that in general, the direct air capture involves trade-offs with the choice of low carbon energy being the most significant to achieving climate benefits, and really just being careful about energy choices in the embodied emissions in all of those energy flows that go into building both the energy plant and the direct air capture plant that's coupled to it. And I'll end here, which is, it used to be a decade ago, to meet climate goals, we could simply think about how do we avoid carbon in the first place, and that's energy efficiency, low or zero carbon fuel sources, conventional CCS, all of these approaches. But the climate models are telling us we're no longer there. And so now we're in a different world where we really have to think of a broader portfolio than we used to, and that broader portfolio is going to include negative emissions and not just natural solutions, but also technical solutions like direct air capture.
All right, thank you, Jennifer. And lastly, we have two shorter presentations from kind of our case studies for today. So we have Jeff Holmes first, and then we will have Keith from Clean Energy Systems. So Jeff, go ahead.
Yeah, thank you, Jordan, and thanks to Air Resources Board for both for holding this hearing and for inviting me to speak at it. I think it's incredibly important, especially in light of conversations that are going on around the world about deep decarbonization and emissions mitigations right now. And I mean, on a personal note, I've noticed it's very easy to have a target of net neutrality. It's a lot harder to have a plan that gets you there. So I think the work that this team is doing within Air Resources Board to look at a full roadmap to carbon neutrality for California is immensely important. So look, a lot I think has been said about direct air capture already. I'm sure I'm going to repeat a few things, but I'll keep my remarks a little bit short so we can get to questions and answers. I think what I'd say, we're one of the leading DAC developers around the world. We've been working on this. Our company was founded in 2009, but a group of us were working on direct air capture before that as well. And our mission since the get-go really has been to develop and then commercialize direct air capture at an industrial scale. And those last few words are really important as they sort of dictate both the technology strategy and the process that we've ended up with, and also our trajectory to market. So what we've really tried to do to manufacture a technology that can be deployed at industrial scale, where it really makes sense within the energy system and the size that the energy system operates at, and really can make an impact on climate goals as well. We've chosen a path to go out and try to find equipment and chemical processing steps that already exist in other industries. And of course, to adapt and innovate and re-engineer those pieces of equipment and those steps to form an air capture system. But we've really wanted to work with equipment that comes from other industries, because we can buy it at known prices and from reliable vendors, and we can deploy it with relatively low risk that it will fail or underperform. So what we've ended up with is a system that uses essentially modified cooling towers to bring very large quantities of atmospheric air inside a device that we call an air contactor. And it meets up with a liquid capture chemical that chemically wants to react with the CO2 that's in the air. So that by the time we return the air back to the environment, it's got about 3/4 less CO2 in it. So we take it from about 400 ppm down to about 100, and we vent that back to the environment. And what happens is that CO2 reacts with our capture chemical to form a salt. And so one thing that's really good about that is we have solutions that are non-volatile, really fast kinetics. So we're actually able to capture a lot of the CO2 in a low depth. The solutions aren't volatile, so they don't emit water vapor. But the challenge is that we end up with a salt solution that then has to be processed. And what we want to do is extract the CO2 back out in a purified form and also remake the capture chemical if we can, so that we avoid chemical repurchase or intake. So what we do, again, with equipment that we've borrowed and adapted from other industries, we have a device called a pellet reactor that precipitates our salt out of solution. We've borrowed this from the water treatment industry, and we basically make pellets of calcium carbonate. So that's the same mineral that's in your teeth. It's the mineral that makes up eggshells or limestone. And when you hold those pellets in your hand, you've about 50% of the weight, so half the weight of those pellets is CO2 that we've captured from the air. The other 50% is calcium that was in our system already. So we've taken CO2 that's in the air at about 0.04% concentration. We've brought it up to 50%. And what we then do is fire that in an oxy-fired calciner, which is really a fancy industry term for a furnace. And when those pellets reach a certain temperature, they give off their CO2 again. And the reason that's important is because we take that vessel, that oxy-fired calciner, and we heat those pellets up. They give off their CO2. We also get some more CO2 and water vapor from our energy sources, which I'll talk about in a minute. But we get this very pure CO2 stream in the headspace of that vessel, which we can then take to gas cleanup and compression, where we knock out any particulates and any water, and we end up with a pure CO2 stream. Now, when the CO2 comes off those pellets, you're left with a product that's called calcium oxide, which once we mix that with our makeup water, actually helps us remake the original capture chemical. So really the takeaway here is that we're able to run a closed chemical loop that takes energy and water and air as inputs and produces pure CO2 as an output. Now, to come back to the energy, to go back to some of Jen's points about how we both power these facilities and how we address trade-offs between land use impacts and scarce resources like renewable electricity or others, this process can actually be powered by natural gas in a way that the gas combustion doesn't result in release, so that we capture the combustion CO2 along with atmospheric CO2 and deliver both. Or it can be powered with a mixture of renewable electricity and natural gas, or entirely with renewable electricity, but we're a little earlier on the technology readiness scale there. So that's not what we're going to market with, but it's something under active development and engineering at Carbon Engineering. And so really what I want to do is just talk a little bit about our path to market and the readiness of this technology and a couple of different use cases that I think are quite relevant to California's goals of reaching net neutrality. So I mentioned that the company's been around since 2009, and we've actually piloted the whole direct air capture process. So we've piloted the capture, the precipitation, the oxy-fired calcination step, and we've been running a pilot that does all of those operations since 2015. So like I was alluding to with the industrial precedent, we know this equipment works and we know how it works, quite frankly. And as investors and other partners have come into the company and joined our team, every one of them has said this technology is ready to scale up. It's ready to go to market. So what we're doing at the moment, we're building an additional set of equipment at our facility up in Canada. That's going to serve as a long-term innovation center. The equipment's getting a little more sophisticated, a little more ready to run 24/7 operations and help us learn about some of the more sophisticated process controls that our team's going to need to run large facilities that interact with variable weather and prevailing winds and those kind of factors. And we're also in early engineering phase for a large plant that's targeted for the Permian Basin. with our partners, Oxy Low Carbon Ventures, which is a subsidiary of Occidental Petroleum. So what I want to do is talk about this plant a little bit. We announced it in partnership with Oxy Low Carbon Ventures back in May of this year. And we announced this plant and the fact that it was going to have a capacity of about 500,000 tons. So Jen was mentioning earlier that air capture's really only been deployed at the sort of 1,000 ton per year scale. And due to the fact that we've been working on a technology that really works best at 500 kilotons or a megaton of CO2 per year, and due to the fact that we've been working on that for 10 years and are now making this leap into the commercial space, we're ready to deploy a facility that's much, much larger than what has been done before. So we're getting into early engineering for this facility, and like I mentioned, this is targeted for the Permian Basin, where there's a lot of existing infrastructure that does enhanced oil recovery, where historically CO2 has either been produced or purchased and injected into reservoirs to enhance the oil production. And a lot of those were operated under the paradigm that carbon dioxide was a cost and oil was a revenue. So you'd like to minimize purchase of the former and maximize production of the latter. And I think what's really important to note, especially in a policy context at Air Resources Board, is policies like the low carbon fuel standard and the inclusion of direct air capture and CCS within that standard are actually going to change the economic paradigm under which a lot of these producers operate their fields. So now you're no longer just paying to inject CO2 and getting paid to produce oil, but you're actually getting paid for the net atmospheric CO2 you are able to inject and store, as well as getting paid for oil. So that really opens up a whole bunch of new prospects over how these fields are used and how they're used to safely store atmospheric or captured anthropogenic carbon dioxide, and used as kind of the first vaults, so to speak, for carbon capture from different sources. So that's what's happening with the Permian Basin project. I mentioned it's in early engineering now, and it's slated to come online sometime in late 2023 or early 2024. I think this is really relevant, especially to these discussions at Air Resources Board, because this is a typical project cycle for an energy project. It's very, very typical to have a few years of engineering and a few more years of construction before the project even runs. And when we were talking about deep decarbonization or net neutrality a couple decades away, that's really not a very long time from now. And frankly, as someone who's kind of worked on the bitter end of trying to pull projects like this together, it really says that now's the time to start. Now's the time to start on the industrial emissions, on the transportation sector, on carbon removal through DAC, and frankly, all of the above. I'd like to talk a little bit about a couple of other use cases for direct air capture and ways they can help carbon neutrality. Frankly, I think this is the most simple scheme in which air capture could be used. We sometimes call this standalone negative emissions or standalone carbon removal. And it really refers to the use of air capture paired with permanent geological storage, but completely uncoupled from any oil or hydrocarbon production. And I think it's really important to talk about this a little bit because the EOR industry in the United States is pretty big, but it's not that big. It's a lot smaller than the quantity of fossil carbon emissions that go to the atmosphere. And if we're really going to get to deep decarbonization and net zero or even do net removal one day, we're probably going to have to scale removal and storage up to larger volumes than what EOR has done in the past, which means we're going to need more storage resources, some of them in saline aquifers, others in depleted or abandoned oil and gas reservoirs, whatever it may be. But really, this standalone removal is just kind of about pairing direct air capture with geological storage to do removal and removal only. And I think that's getting to be really interesting, especially as we're seeing corporate actors like Stripe or others put out goals or statements that they want to move beyond traditional forms of offsets and start doing physical and verifiable and permanent carbon removal. We're going to have to look at schemes like this. So the numbers on the slide here are not meant to be a super exhaustive or detailed LCA, but they are meant to reflect the kind of emissions that such a standalone negative emissions facility would incur. So again, this isn't fully transparent and published yet, but it does use pretty standard emissions factors from California GREET, and it tallies up the kind of emissions that would be incurred by a gas-fired direct air capture facility going straight to standalone injection. The answer is that for about every ton of CO2 we capture from the air, this facility in this configuration would emit something like 0.1 tons of CO2 and thus achieve net storage of the other 0.9. So at least to me personally, that seems like a pretty good deal. I think the other couple of things just to call out about standalone storage, Jen mentioned earlier, we have to consider land use impacts, and I couldn't agree more. You're not going to cite facilities that take several hundred acres and filter carbon out of the air in the middle of dense urban or residential areas. So really, I think prospects lie in pairing these kind of air capture facilities with marginal or non-arable land in places that the geologic resource enables provision of both energy and then storage of the CO2. And frankly, in that configuration, these facilities can capture and store quantities of carbon dioxide that would require land areas several hundred times greater to do with biomass. So there's a really central trade-off here, I think, between sort of cost and permanence of geological storage against, potentially cheaper, but also less certainty around permanence and certainly far greater land use with some of the biological-based approaches. The last thing I wanted to mention real briefly was another way that air capture can help us get to net neutrality, and this is enabling synthesis of renewable fuels. So we heard a lot about intermittent renewables and great renewable development in the renewable sector recently, but renewable power isn't always best produced where and when it's needed. There's plenty of parts of the world that have great renewable resource, but not global demand centers for energy and that aren't linked easily by pipelines or transmission infrastructure. And so this concept of pairing air capture and renewable power generation where it's cheapest to make renewable hydrogen and capture CO2 directly from atmospheric air, and then use the two for a thermocatalytic process called Fischer-Tropsch, allows us to take that renewable energy and harness it in a stored form and also a form that's compatible with today's infrastructure and refining assets and in-vehicle engines. So it's a concept we call air-to-fuels. Obviously, when powered by clean electricity, these fuels have far, far lower life cycle carbon emissions than conventional fuels, and they burn a lot cleaner as well. So we think that's an important complement to EVs and some of the other technologies that are already decarbonizing transportation. So I think I just end by saying, California is a great place to scope out a pathway to carbon neutrality. California's got, I think, some of the best tools in the world in the form of the cap and trade program and the LCFS and, a really active body like Air Resources Board and others like the California Energy Commission. And I think we're just going to have to collectively keep thinking about these tools and how to modify them to make sure that we get carbon removal and carbon capture at source, both into the marketplace and to scale as rapidly as we need them to. We're out on the fringe of financing a direct air capture facility right now, trying to raise hundreds of millions of dollars of capital. And frankly, there's a lot of investor and lender hesitance about programs like the LCFS. It may seem to be carved in stone here in California, but I don't think that view is shared everywhere. So I think, proponents like ourselves are sort of finding some of the wrinkles or some of the challenges that we're going to have to get over to finance, multi-$100 million facilities, and eventually many of them on the back of policies and regulations like the LCFS. And I think one of the smartest things we can do is keep looking at how to use the tools we've got from a policy perspective. So thank you.
Thank you, Jeff. And Keith, the floor is yours.
Okay, thank you, everyone. It's a pleasure to be here, and I'm looking at the clock and realize I have minus 20 minutes to give my presentation. So when talking about negative emissions technologies, I guess that fits a little bit. I want to talk about our carbon negative energy projects, or C&E, also known as BECs, which we've heard about, and the production of renewable or green hydrogen from these projects we are working on in California. With the first slide, we've already talked, this has been covered a bit already. We're focused obviously on carbon removal and very specifically C&E, or bio-CCS. So the CO2 is going from the atmosphere into the trees. They're going to be used in the process plants with full carbon capture, and that makes them carbon negative. We've just heard from Jeff about direct air capture. We refer to this as indirect air capture, where you have the benefit, in addition to pulling CO2 out of the atmosphere, of producing a transportation fuel. It could be green hydrogen or renewable carbon negative electricity. To talk a bit about the process, on the left side, the inputs are basically CO2 from the atmosphere into the trees. The tree becomes, or the ag waste, to be quite clear, we're not talking about planting crops in order to produce fuel. So this is existing ag waste or green waste from landfills in California. They go into a gasifier, and in that gasifier we produce a syngas, a biogas. That gas consists of hydrogen, methane, carbon monoxide, carbon dioxide, and from that gasifier and in that syngas, we extract and separate out the hydrogen with membranes. So it's all proven technology. Everything in gray boxes is commercially available off the shelf. The hydrogen can then go to refineries. We've heard about huge demand for hydrogen in refineries. So this is now green hydrogen replacing hydrogen from natural gas with CO2 emissions. The residual fuel we call hydrogen depleted syngas. That's where all the carbon is. It's in CO2 and methane, and that we combust with our pressurized oxy-combustion technology. I fully agree with Jeff that now's the time to be working on these projects. Unfortunately, we started in 1993, so we were a little bit ahead of the curve, but it's good to see real progress now. So this technology was developed here in Sacramento, where our founders worked at Aerojet over in Rancho Cordova, and the power block is essentially a modified rocket engine. So we burn with oxygen and fuel, hydrocarbons, and what we get is steam and CO2, and that's used to power turbines, and we produce electricity. At the end of that, we capture all of the CO2. I'll show you that in a little more detail on the next slide. And the electricity in our plants that we're working on is really to run the process. We're putting the energy to the market, to the transportation sector as hydrogen, so that we don't have to deal with base load power purchase agreements and interconnects and the other things that go with selling electricity. We can do it, but we find the hydrogen path to be a bit easier. And then the CO2 is sequestered. So when producing hydrogen for the market, for every kilogram of hydrogen produced, we're putting about 75 kilograms of CO2 into the ground. And when that hydrogen goes into a hydrogen fuel cell car, you drive a mile and you pull 3 pounds of CO2 out of the atmosphere. So, and it's about the same if electricity were produced instead of hydrogen. We could forego the extraction of the hydrogen and simply make more power and sell that. And then for the EV, you drive a mile and you pull 3 pounds of CO2 from the atmosphere. So a little bit on the power cycle. Again, it's oxygen and fuel going in. The fuel could be hydrogen or hydrocarbon. In this case, we're talking about the hydrogen depleted syngas. If we work with fossil fuels, we're carbon neutral, but we definitely see the path for reasons that have been talked about, linking to the transportation sector and going carbon negative by working with the biofuels, the biogas. So when we combust, as I mentioned, it's think of a rocket engine. Space shuttle main engines burn hydrogen and oxygen. It's essentially steam that was coming out of those three engines. And if you took two space shuttles and piped exhaust to turbines, you could run the state of California. So there's very, very high power density, and that's basically what we've done. The equipment shown in blue, we've built and tested. It's at a scale where it's about 1,000 tons per day of carbon capture, and that we've run for short duration on a continuous basis. We've run at 100 tons per day for thousands of hours, making electricity connected to the grid. The steam and CO2, again, that's produced, it's a high temperature, high pressure gas. It drives turbines, produces electricity, and then at the back end of the cycle, we can do some heat recovery, and then the steam in the drive gas is condensed back into water, and it naturally separates from the CO2. So we're not requiring absorbers, chemicals, and the other things that are necessary for direct air capture. This is a simple phase separation that you get when you do pressurized oxy-combustion. Net Power is another company that's doing similar technology and similar results, but we chose to work at lower operating pressures, working with steam and CO2 instead of supercritical CO2, because then we can use technology that's available today. The CO2 then, once it's extracted, it's separated from the water, is compressed and stored in geological formations. Our projects are all focused on saline sequestration, not using it for EOR, so we can decouple from oil prices, which has been a real obstacle to getting CCS deployed over the last several decades. We get projects ready to deploy. When oil was $100 a barrel, there's high interest in CCS. When it dropped, the interest just completely went away. So that gets to why now, and it ties to this program. It ties to LCFS. We've been working these projects for a few years, and 3 years ago, the value of capturing CO2 and putting it in the ground in California was $20 a ton. You would get the 45Q credit, which back then for permanent sequestration was 20, and in 2018, it was increased to $50 a ton. The big change, of course, has been full implementation of LCFS. While it was there a few years ago, the industry wasn't buying in. It would stay permanently in place. It was expiring in 2020, and when we talked to the oil producers in California, they basically say we just discount it. So there's no value on long-term projects for those reasons. When it was extended to 2030 and litigation ran out, the program is clearly in effect and it's biting, and the value is roughly $200 a ton. So you take the increase in 45Q to $50 a ton plus LCFS, and what happened is the carbon capture and storage market, when linked to the transportation sector, went from $20 to $250. So these projects make sense today, assuming your cost is below $250 a ton, obviously. The second factor that ties into this is over the same time period, the biomass industry in California has collapsed. When biomass power plants, when their PPAs expire, they go to renew under renewable portfolio standards, and they compete with wind and solar, and they lose every time. Wind and solar is 4 to 5 cents, and biomass is around 9-10 cents a kilowatt hour. So half the biomass plants in the state have closed, so you have assets that can be repurposed, and you have low-cost inputs on fuel that's available for very low cost. The third piece that's required is a technology to link the two, and we have been working on it for 25 plus years and have put about $135 million into getting the equipment and the technology ready. It was actually ready in 2014 timeframe, and when the oil prices dropped, the CCS industry just basically was parked. So the LCFS program and linking to the transportation sector has allowed it to really move forward and get deployed. So when we look at today and what the vision is for tomorrow, today half the biomass plants in the state are closed, and the intent is to get them back online and repurpose them as green hydrogen plants. They're also really CO2 processing and removal plants. You can think of the hydrogen and the electricity as byproducts to the main purpose, which is pulling CO2 out of the atmosphere. Biomass plants have criteria pollutants. There's NOx particulates. The oxy-combustion cycle is near zero atmospheric emissions. So you also eliminate all of the criteria pollutants associated with burning biomass, even in power plants. Today, because the biomass plants have closed, we have open field burning. The air quality in the Central Valley is the worst in the country, and it's getting worse because we have no place to put this ag waste. So we will convert that instead to renewable green hydrogen. Natural gas today is used to make hydrogen. Jeff talked about that. We consume a lot of gas to make a lot of hydrogen for the refineries. We can displace some of that with this renewable hydrogen from the ag waste. And then we have the tree mortality issue and the wildfire crisis. So we have 100+ million dead trees. That's perhaps a future phase, but it's another problem to be solved. And you can only solve it if you have a place to put all of that carbon rather than the atmosphere. Final 2 points, biomass plants today consume water. Oxy-powered cycles, oxy-fuel cycles are net producers. You have hydrogen in the fuel and oxygen from the air, so you make water rather than consume water. And then you can, if you're sequestering CO2, you can pull saline water up, brackish water, and process that to provide industrial water for agricultural purposes. We've talked about storing CO2. If you're going to capture it, you have to store it. And the good news is the Central Valley of California has about 1,000-year inventory for storing all the CO2 from all the point sources in the state. So it happens to be an excellent location for sequestering CO2. These two maps overlay where the storage sites are and where these idled biomass plants are. The green on the map on the left is where you would want to store CO2, and the yellow circles are plants that are currently shut down. So there is an excellent overlay of, again, getting these plants back online, creating the jobs without the pollution that was associated with them. They also happen to be perfectly located for the hydrogen highway. I think we could leave most of this for the Q&A, but there are ways we can improve. Really, it's fast-tracking the CCS project. It is time. They are economical under the right circumstances. And we've heard from Jeff about having some predictability on LCFS pricing, floor pricing, or some other certainty will be helpful. And then really, I think what's going to happen is we're sort of testing the LCFS regulations. Are they perfect today? No. Can they be structured so that we incentivize and accelerate good projects? I think the answer to that is yes. The last slide, trying to take advantage of the negative 20 minutes, is the environmental impact. So we're currently working on 4 sites that we have site control. They range from Bakersfield up to Fresno area. And these plants, the first will go online in early 2022. We're currently working on the Class 6 CO2 storage permit, and that will be ready to submit this month to the EPA. So it is a real project that's really going on. And from those first 4 projects, we'll produce about 33 tons of green hydrogen, and we will remove about 1.3 million tons of CO2 from the atmosphere. There's also criteria pollutants that are avoided because we're not either open field burning or burning in biomass power plants. The potential for the state, if you were to retrofit the biomass fleet, is roughly tenfold of what we could do with these first 4 plants. So you start to get to meaningful numbers. Jeff had the slide. I think it was 64 million tons per year from industrial and power plant sources in the state. And if you just retrofitted these 50 plants that are already built and they're near the feedstock sources, you could get about 16 million tons of CO2 coming out of the atmosphere. So it's a great way to start. They're not mega projects. They're 100 to 200 million, not billions. And again, they're ready to go now because the technology has been built and tested, and it's directly linked to the transportation sector. So with that, I thank you.
All right, thank you, Keith, and thank you to our entire panel for those presentations. So we're going to move into our panelist questions now, and we are mindful of the time. We have a hard stop at 5 o'clock, so we will be sure to open things up to the audience soon. I do want to direct a few questions to particular people on the panel, but even if I don't say your name directly, please feel free to jump in. We'd like to encourage a lively discussion here among the panelists. So I'm going to go ahead and direct the first one at Keith and Jeff Holmes. So it's clear that large-scale deployment of capture technologies and carbon dioxide removal technologies are going to be necessary to meet our deep decarbonization goals. So what are the biggest barriers to near-term deployment of carbon capture technology? And what actions can industry and policymakers undertake to overcome these barriers?
Yeah, I'll take that at least to start. I think in our particular case, the real barrier or risk that comes up, there's really two. One is, can you get a permit to store CO2? And related to that, since it's tied to LCFS, is the permanence protocol. So being able to link those and make sure that can go rather quickly is going to be helpful. The other issue is, again, that uncertainty on LCFS pricing. It's near the ceiling today at $200 per ton. But the investors in the projects, they want to know how's your project when it drops down to 100 to 75 to 50, even if the market is saying that's not likely to occur. I think those are the two biggest pressing issues that we see. We do have a natural gas project with CCS that we're working on, and I mentioned about the regulations and not having them fit every scenario. They didn't anticipate every project that might come up. So having some flexibility around finding a way for good projects that reduce carbon intensity of natural gas or oil going into refineries, that would be helpful as well. But we're making good progress on all three fronts with those.
Yeah, I think I'll echo some of that. I think, to Keith's point, there's a lot of proponents out there, like both of our two companies that are sitting here as case studies. There's people who've been working on technologies or on projects for over a decade. Like both of ourselves, there are technologies and there are ideas that are ready to go. And I think, frankly, it's easy to forget sometimes that the CCS protocol came into force in January of this year, right? I mean, it feels like a long time ago, but it's not a long time ago. And frankly, prior to that, we just had insufficient revenues to pull capital into projects and to get going with projects where revenues exceed costs. My colleague Jen here was on the National Academy of Sciences panel that took a look at direct air capture and a bunch of other carbon removal technologies. And they came away and concluded that there's really no limit to building out DAC facilities and to scaling them up. And, frankly, it's a pretty similar case in flue stack capture as well, but that the economic limitation was really the only constraint for DAC. So frankly, having the LCFS move forward and having the CCS protocol come into force has just been a total game changer, and has greatly increased the revenue stack that we can build together to get a project to go. But frankly, I think we're all still collectively figuring out both how to move forward and apply into it and comply with it, and I think figuring out how to implement it as well. And I think I alluded to this very briefly earlier, but just to sort of build on my remarks a little bit, colleagues of mine at Carbon Engineering are out talking to investors and lenders, trying to pull this Permian project together. And one of the things we have to do to give them certainty that the project's going to work and that the revenue is stable is we actually have to go out and try to sign an offtake agreement for at least some of the LCFS credits that our project would generate. And as you might imagine, if we are looking to sell some of those credits on a long-term offtake to an obligated party or some kind of credit trader, they're not going to pay full face value. They're not going to pay the full value that's in some consulting forecast or the value that we see in the latest monthly report. So there's a big discount there. So I think it's really just recognizing that there's a lot of commercial and business realities that have to come into place underneath the technological and the policy realities. And I think it's also recognizing that the primary job of the LCFS or the cap and trade is to pull more of the existing clean technologies into the market. But it should also be to incentivize development and commercialization of new technologies as well. And some of those are either going to require a little bit different treatment or a little bit of help to get investor capital in as they get through their scale up and technology risk retirement phase. And I think it's all just about sort of our community looking to these commercial and business realities that proponents like ourselves face and making sure we overcome those to get actual projects in the ground and then to get CO2 flowing underground.
You know what I think is that it's the biggest obstacle, if you go up a little bit of a higher level, is menus with no prices. I mean, when I was a kid, because I'm pretty old, they still had things where you go out on a date and then your girlfriend, they'd give her a menu with no prices. It was kind of weird. It's like, well, we do this with the public. The carbon capture, the International Energy Agency says that ultimately the developed world, rich countries are going to have a price per ton on carbon somewhere around $100 to $120. So anything that we can do now that's somewhere cheaper than that, $40, $50, $60, we should be doing it fast. And I think part of it is we all have to do a good job as we talk to environmental groups and policymakers of saying, the earth is going to cook. Anything that's cost effective, whether it's aesthetic or non-aesthetic, it looks tricky or non-tricky, we got to do it now. And, my example of that is of sort of muddy thinking is there's a big deal about, wow, could you really put carbon capture on one of these things called a steam methane reformer? It's how you make hydrogen, right? The thing I talked about in the refinery. Wow, could we really do that? Gee, that's hard. Every single fertilizer plant in the world that uses natural gas as a feedstock to make fertilizer basically already has 50% carbon capture. Why? It's because first you make ammonia, then you grab some CO2, you stick it together, it makes these little granules called urea, and then you can stick it in your green Scott's fertilizer spreader in your backyard. The point is, normal industrial process, they have 50% carbon capture. Nobody talks about that, and somehow it's a bunch of drama if you do it on the exact same machines, the exact same kit, a steam methane reformer at an oil refinery, instead of the same thing at a fertilizer factory, right? If it works, and if it's somewhere under $100, we're supposed to do it now, or else we'll be chasing our tail in 50 years with things that are much, much, much more expensive. That's my 2 cents. Give people a menu with prices.
Thank you. Anybody else want to weigh in on that? Okay, let's move to the next one. So Lee, we're going to start this one with you. So the LCFS, as you mentioned, is focused on the transportation sector. What policy mechanisms are needed to incentivize adoption of capture technology outside of the transportation sector?
Thank you, and I don't want to repeat what I already said in my presentation, but instead give also the chance to my fellow panelists to chime in. I mean, I think 45Q, as said multiple times, is a very significant incentive. And beyond this, I mean, optimizing it so that there could be CCS-specific incentives beyond the transportation sector in California is one way. Demand side, procurement strategies, pathways. I mean, we're talking SB 100, obviously. So integrating CCS in that clean energy standard, defining it as a resource eligible is another way. And then really focusing on optimizing how we can get projects done within the next years to have them eligible for 45Q. So really potentially additional financial incentives to incentivize investment and also support for infrastructure build out. And I want to hand it over to my fellow panelists at this point.
One quick thing. It's just kind of odd. It's good that LCFS is at $200 because that will engender a lot of work, but it's kind of odd to have roughly a tenfold difference between the value of a ton of CO2 avoided in cap and trade, right, at like sort of $17, multiply by 10, you know, 170, $200 in the liquid fuels sector. So somehow or other, a little bit, it's almost like it's an overshoot on the LCFS side and a huge undershoot on the cap and trade side, because there's a lot of things that will work at, you know, 30, 40, $50, but they're homeless, like cement, no place to go.
Yeah, if I could add to that, I completely agree. And that's one of the reasons, again, we sort of pivoted and said, let's focus on how we link carbon capture to the transportation sector because the revenues were there. But to expand it and to perhaps solve that problem and going to the menu without a price option, what we've talked about so far is trying to figure out what's the right price for it to work. But the only reason wind and solar, well, not the only, but a main reason wind and solar is 3 or 4 cents a kilowatt hour today is it was 20 cents and 40 cents a kilowatt hour in the past, but there were portfolio standards. So there was market demand by a portfolio standard that said, you know, the utilities need to buy X% as renewables. And no matter how much it costs. But they didn't say buy 100% of it at that high price. They said buy a few percent. And we advocated some time ago for a low carbon fuel portfolio standard that said, okay, you have X gigawatts of fossil fuel in California. Let's start with 5% must have CCS or DAC to offset, and the cost will be the cost, but make it competitively bid, and you will introduce CCS into the power sector, the non-transportation side, at the lowest cost. It may be $40 or $50 a ton, it may be 80, it may be 300, but at least projects would have, there would be a market, and that market demand is what's required in order to get the cost down. A lot of work's been done about paper plants at $30 a ton. We can get there, but not if you require the first plant to be at $30 a ton. That would be like waiting for wind and solar to be deployed. You know, we'll buy it when it's 4 cents a kilowatt hour. Come and see us then. It never would have happened.
I'll chime in real briefly as well. Just I can't resist on that topic. I mean, the other thing to say about wind and solar is we never got thin film solar, right? We never had that light bulb moment in the lab where miraculously things got 5 times cheaper. We just got incrementally better at doing every piece of the supply chain. And so I think, you know, there is a bit of a prevailing mindset out there that you put money into R&D and better technological goodies come out that are cheaper, and then this whole problem becomes easier. And I think that certainly has merit, but so does the parallel path of deploying what we've got and getting incrementally better at things. And I think, you know, easy to articulate the idea, harder to implement, but I think the concept of some kind of graduated pricing or some kind of premium for technologies that can accomplish strategic goal X, Y, or Z, start pulling them into the marketplace, start to see how they really deploy, what they really cost. And then, you know, you do the bulk of your emissions mitigation on the margin with the existing programs that are out there. But I think we need to get creative.
Thank you. Okay, my next question is directed to Ben and Jennifer. Ben, can you hear us?
Yep.
Great, all right. So we're going to look at utilization with this question. So what are the best uses for captured CO2 now? And how do we support targeted capture and utilization while transitioning to permanent sequestration?
I guess I'll go first.
What are the best utilization opportunities now, or what are the best sort of opportunities for what to do with carbon generally? I mean, I think economics suggests that EOR is, at least it's popular in terms of what to do with captured carbon. I think, you know, the air to fuels concept has great long-term potential. It relies on a pretty heavily renewable grid that we haven't really reached yet. So I think sort of in the 2030 timeframe, air to fuel starts looking pretty popular as a means of balancing the grid with high renewable penetrations. You know, a lot of the utilization opportunities are really a little bit longer term that we've seen. So I can't really speak honestly to some of the nearer term opportunities there.
So Ben, to follow up on that briefly, what do you think the role of EOR should be right now?
I mean, I think EOR is a great glide path for us to figure out all the ways that we're going to need to capture carbon in a low carbon economy. And if it's envisaged as such, I think that's the fine use for it. I mean, it's certainly not the end goal, obviously, right? I mean, and I don't think anyone is really sort of thinking it is that. But it provides another sort of, you know, I've heard the term revenue stack. I think it's an important way to get these across the finish line in terms of financial value and start us along the path of technology deployment. So I'm certainly supportive of its use there.
Yeah, I'll follow up on that. So I agree with what Ben said about EOR. I'll just talk a little bit about utilization in general. So the utilization market for CO2 in the US is on the order of about 80 million tons of CO2 per year. 70 million tons of that is EOR. So we've looked at a lot of things of like, what do you do with the CO2 once you separate it? We've looked at the food and beverage industry. It's about 3 million tons of CO2 per year. The benefit of the food and beverage, and I'll talk about timescales in a minute, but the benefit is that, you know, if you have a Coca-Cola plant or even more like a Polar or a microbrewery, they may be paying up to $400 per ton of CO2 for high purity CO2. It's a small market, but so are some of these first stage plants that you're building. And so it's not too bad to look at the coupling. They're also ubiquitous. They're everywhere in the US when you look at these plants. And where are the Coca-Colas getting their CO2 today? If you fly over any of the refineries, you'll see a Coca-Cola plant sitting right beside it, you know? And it goes back to a little bit what Jeff said before. When you're at an oil refinery, you need to make hydrogen. And when you make hydrogen, you inadvertently make 70% purity CO2. And so when you have a stream that's 70% pure, it's pretty easy to take it the rest of the way. And in fact, they produce more CO2 than they know what to do with. And the beverage industry, the neighboring beverage industries to refineries aren't enough in order to take all that CO2 on. And so I think, you know, looking at opportunities like that, but we do have to be careful and recognize that is not a solution to helping climate, right? The CO2 is going to be re-emitted in the atmosphere as soon as you open your carbonated beverage and drink it. But the idea of it paying for the plant to begin with is interesting, you know, so it's actually helping to get the deployment going. But again, everything outside of EOR adds up to about 10 million tons of CO2 per year in the US. The EOR, I do have a view on that, in that today, of that, say, 70 million tons of CO2 for EOR, 80% of it, the CO2, is naturally sourced today. So there's like some other steps that we need to do, and that is stop using naturally sourced CO2. You know, in our research, we've done studies, we're looking at, well, where are the existing CO2 pipelines? Are there anthropogenic CO2 opportunities not far that one can look into? And absolutely, there are a lot of opportunities, both industrial CO2 and also natural gas-fired power plants where you could retrofit with carbon capture. there are options that are a lot cheaper than direct air capture as kind of a first step to coupling with EOR. But ultimately, coupling, direct air capture with EOR is another opportunity. The other thing I'll say is, as a segue, today we have 45Q up to $35 per ton for EOR, $50 per ton potentially for geologic storage. But if you look at the geology of where depleted oil and gas reservoirs are, depleting oil and gas reservoirs, and you look at the geology, a lot of the formations in the earth are in this, layers, and some of the pore space in the sedimentary formations have oil and gas, and some just have salt water. And so there are opportunities called like stacked storage is the term, where you could imagine if you're an oil and gas company and you're doing CO2 EOR, you have one well here and it's for CO2 EOR, and you bring the oil to the surface, you separate the CO2. Rather than re-injecting that CO2 back in, you have a dedicated storage project. And you could envision that oil companies are becoming carbon sequestration companies over time. And the jobs are quite similar in terms of oil and gas and carbon sequestration. So I think there could be a transition, but the policies have to be written very carefully so that we're not doing, we're not kind of exploiting carbon capture just for enhancing oil recovery and have it be that's the only story.
I just wanted to add to this, and I agree with what you've said. Enhanced oil recovery, there are now 10 operating large-scale projects in the US, and 9 of them use EOR to sequester the carbon. Just one is geologic storage. And going forward, we expect this to change because obviously we have upped the value on geologic storage via 45Q. But I also want to highlight that there is an emissions reductions benefit to CO2. The International Energy Agency had put forward that there is a 37% emissions reductions of the life cycle of the barrel of oil produced. And as such, moving forward, recognizing that enhanced oil recovery has played a big role in incentivizing this first wave of CCS projects in the US, I think it will still be a role going forward, will still have a role going forward. And we need to recognize its role in reducing the life cycle emissions, but we'll also see more geologic storage projects going forward. And then I also want to say the question, the way it was framed, was that it was utilization versus sequestration. And thinking of non-EOR use, I don't think these are two areas that are mutually exclusive, but rather it's and, because the scale of CCS deployment that's necessary within climate goals eclipses the scale of utilization possibilities today. And as such, gigaton scale geologic storage is extremely important.
And following on what Lee was saying too is, think about it, we've got a classic pollution control problem where the better you try to get, the more of the pollutant you try to capture, the more expensive it gets. I mean, I spent a lot of my time financing sewage projects, and first we had primary, and we got better, and we had secondary, and we had tertiary. As you went along, it got more and more expensive. Well, right now, we've got public policy really in the US where we don't even admit that CO2 is a pollutant. So we're trying to ramp up these technologies, with duct tape, string, and baling wire. So guess what? At the first of it, as you get going, we're going to have to find the very cheapest carbon capture opportunities, and inevitably, we're going to need to get some revenues to pay for these technologies from enhanced oil recovery because they're the only paying customers. So it's not very aesthetic. None of us want to get any more fossil fuel, but it's the only way to get deployed. In the next stage, we're going to have medium concentration, more expensive capture. We're going to run out of revenues from enhanced oil recoveries, so we're going to have to pay for sequestration, right? So our cost went up and our revenues went down, and eventually we're going to be having to hit direct air capture, where we have very low concentrations and, again, passive storage. That's okay. That's a natural progression. But I think we all have to get our mind around, we got to start somewhere, and it's an emergency, and we might as well start, with the cheapest capture and anything where we can get a nickel from the CO2 just so that we can get deployed and drive costs down.
All right, thank you all. So looking at the time, I think be a good time to open things up to the audience or to people that are listening in as well that have called in. So welcome you to ask any questions to our panelists. And we'll bring microphones around in 1 second.
Hi, thank you very much. Frank Harris with California Municipal Utilities Association. You talked about it at this in response to the very last question, but I think it sort of buried the lead here. Carbon capture is interesting, technologically interesting, but the policy challenges of the sequestration are extraordinary. I agree that the timeline we're talking about is not very long. And you could say the same thing even if the technology for capture were, say, zero cost right now. The policy timeline is not very long. You try to open up some of these resources in California for pure geologic sequestration, and the list, the line of people ready to make their 3-minute comments to various hearings and city council meetings is going to be around the block, multiple fold. And I'm just kind of curious, perhaps this is a question best for Lee, since you work very clearly in the policy space. How do you address that? How do you go about thwarting that challenge? Thank you very much.
Can you, what challenge exactly do you mean?
Public policy challenge.
You mean additional, what policies are needed?
Public policy challenge to get the permitting required and get the authority to do the geologic sequestration. The NIMBYism is going to be overwhelming.
Okay, public acceptance. Yeah, so I think from a public acceptance standpoint, I think recognizing that we need all decarbonization solutions is very important, and a lot of education is necessary. And I mean, all I can say is CCS is safe, it's technologically proven, and it plays a significant role in reducing emissions and climate goals. Is there?
Yeah, I'll be happy to address it because, again, we are going through that. And as I mentioned earlier, we do see one of the main risks is how long will it take to get a permit? And some might say we're more skeptical we will even get a permit. What we've done is consultation, of course, with the EPA, with Dogger, and with the communities, with the NGOs over time, because I think the way we try to frame it is you really have 3 choices with carbon. 1, never pull it out of the ground, never use it. But that's obviously not what we're doing for the next several decades at least. So then you can pull it out, use it, and throw it in the air. And that's what we've been doing historically. And then you get criteria pollutants as well associated with that. So the best option is to pull it up, use it, and put it back. And then it is a conversation to really educate people about storing CO2 is easier than storing methane, easier than sour gas. We inject a lot of water. We inject a lot of things into the ground. The only reason we have gas reservoirs is it stayed for geologic time. So in our case, we're working with Schlumberger, which is the world's largest oil services company. They've done more of these carbon storage projects than anybody out there. But public outreach is going to be a key part. And I think it happens, but it is a question of, is it 9 months, 12 months, 6 months, 18 months, or where do you go? The last thing I'll say is that one of the benefits of the Central Valley, I think it would be very difficult to do CCS in the LA Basin or San Francisco. And building CO2 pipelines is why I think it will happen, but how fast can that happen to move that CO2? But in the Central Valley, these biomass plants are in agricultural resource areas. The population density is much lower. And, so we're seeing good support. It doesn't mean, I completely agree, never going to get complete support. NIMBYism is a fact of life. But the consequences of not doing it is obviously, increased temperature, increased climate change.
I'll make a really quick comment on that as well. I think public acceptance is incredibly important. I mean, it's basically put CCS on hold in Germany. But I think one of the nice flexibilities of the CCS protocol is there's not a geographical constraint on where the capture and the storage needs to be done. So it does, and public acceptance really varies dramatically by region to region. I come from Alberta, where we inject acid gas, we inject CO2, we inject wastewater. There's other places that just don't have that public acceptance. But I think the way the policy is written, it lets us go to those places where we can get started. Jen mentioned 70 megatons of CO2 in the EOR industry. A lot of it comes from natural sources. If all we were to do were to cap those natural sources and supplant that CO2 with captured CO2 from flue stack or from atmosphere, that gives our whole cohort here basically a 70 plant runway to scale the technologies up, earn the trust of the public in other jurisdictions, and hopefully expand from there.
And if I could just add one more thing, I think seeing the political leaders, actually take positions on it and support it would be helpful. So it would be good for the governor's office. It would be good for, the policymakers to say that, yes, again, we saw the numbers. If you say we're against this everywhere, you're basically saying you're comfortable in a 2 to 4 degree C world. So it's not as if there's no cost to doing nothing.
And I also just want to emphasize that from the Institute's perspective, we think that CARB really struck a balance between recognizing the need recognizing the need for CCS, but also wider public concerns with the LCFS CCS protocol and the way it's structured.
We also don't have enough money globally to be real picky and to be NIMBYs and express kind of little minor aesthetic preferences. Just the numbers are IEA. It's around, you have to spend $2.5 trillion of new investment every single year to have a hope of hitting our climate goals, okay? If you don't have CCS, the IPCC says then the number more or less goes up to 6 trillion instead of 2.5. Now, I'll give you one more number. The total new money flowing in to all the institutionally managed funds in the world every year is somewhere between 1 and 2 trillion. If you take all the money that goes into all the mutual funds, insurance companies, pension funds, it's about 1 to 2 trillion. We're supposed to spend 2.5 if we don't vote anybody off the island. And if we're prissy and vote CCS off the island, instead of barely being able to make it, we're just, completely dead. You can't pay for 6 trillion a year when you've only got 1 to 2 trillion.
Hi there, Preston Jordan, Lawrence Berkeley National Lab. Maybe a follow-up on the last question about NIMBYism is, and particularly in the California context, given the fragmentation of pore space ownership under an interpretation of very thin case law that is probably owned by the surface owner and not the mineral rights owner, it only takes 2%, 5% rejection of CCS to stop projects, at least saline projects. And the executive branch's aversion, as recently demonstrated to oil production, I would think would suggest there's considerable risk with EOR as being an on-ramp. The executive could come out tomorrow and say, no, we're not going to allow Dogger to pursue EOR. So I think between those two, there's some pretty major impediments. What would be useful in the saline realm might be something like a unitization law. So I'm curious, Ben, if you considered any of these in the pathway studies, or if there was just a presumption that the pore space is available, if it can be utilized. And I'll finish with a trivia question in the spirit of the trivia question that was put out. There is a 250,000+ capture plant operating in California right now. When did it start operating?
Well, I know because I worked at that plant. I started in 1980, but it was built in 1977, and it's still running. It's a carbon capture plant at a coal-fired power plant in Corona, California, and they use the CO2 in the soda ash plant, basically. So, yeah, California's had CCS for a very, very long time, which means I'm very, very old, of course.
Ben, did you want to address that question?
Yeah, we didn't consider any sort of additional constraints like that. I mean, I think it's important to note in the U.S. analysis, California's sort of physical sequestration pales in comparison to the rest of the country, right? It's not that it doesn't have any, it's just that it has very limited compared to where it really exists, really down kind of the middle of the country. And you know, Texas, of course, has a ton of it. So it's not that California won't make any contribution in terms of direct sequestration, but the impact of sort of that type of thing, I think, wouldn't be felt nationally necessarily. I think that the decision to basically allow sequestration places outside of California is really important, because I think California's basically consumption of products, be it fuels or even just carbon credits, is probably more important than its sort of actual geologic sequestration resource to the sort of solution to the problem. So I'll stop there.
Rich Meary, Frontier Energy. First off, nice job, panelists. My question's partly been answered, so I'll try to focus it here. And this has to do with developing a full chain CCS project in California, including the storage element. And what I heard was a need to tweak programs that the state has, Floron, LCFS, adding CCS protocol to cap and trade, maybe adding flexibility to application of the CCS protocol. What I didn't hear until some of my fellow audience members chimed in were the things you have traditionally heard in developing CCS projects, which is pore space, rights acquisition and amalgamation, long-term liability, the trunk pipeline. Are these also still issues and you just didn't get to them, or are they really all secondary compared to really the finance issues that you deal with in working with equity investors and lenders?
I'll go ahead and take that since we are working in California and are going through it in real time. I wouldn't call it secondary, but there's not a lot of sense of getting worried about, are you going to be able to acquire all of the rights that are needed for a particular project if you don't know you're going to get the permit in the first place. So we are, you know, starting with the Class 6 application, which is with the EPA, and then the way to address, again, it's by picking what we believe are locations where the projects are supported, by talking to the communities, and then by having multiple sites. So if we find that there was an obstacle locally, either at pore space rights or something like that, if you have another site, because what we're really speaking about with these projects is storing CO2 in saline formations 8,000 to 9,000 feet down. It's not displacing anybody's mineral rights, or there's really no impact. You can drive up and down the Central Valley and see gas storage fields, and they're next to almond orchards and vineyards and everything else. So it's not to say we won't have a problem, and that's why there's no guarantee these projects can be built. But by going on a parallel path with different sites, we're trying to hope that, again, collectively there's a certain rationality to it. If somebody says, I just don't want it here, but you have 2 or 3 other sites that you could develop on a parallel path, hopefully that helps get the job done. But I'm not trying to underestimate it at all. It's like, it's not going to be, we have nothing to be concerned about. A lot of it goes back to education. A lot of it goes back to, well, we cannot build these plants, and right across the street you're watching open field burning of ag waste going on. It is, I think it's much more real in Fresno, Bakersfield, these communities than it would be in Los Angeles or San Diego or San Francisco. And that's why I think, and the same problem in the Netherlands and Germany is the population density is much higher. Yeah, I'm hoping we can work our way through it. But the first issue is getting the permit application rolling and then being able to have that data to go out and talk in detail to the communities.
Make a real quick comment just from, I think, the direct air capture and for some of the other carbon removal approaches, we've got a little bit more flexibility of location since a ton removed, anywhere on the globe is sort of equal in its contribution to the mass balance of the atmosphere. So again, I think, some of the legal or jurisdictional issues that might prevail in California, quite frankly, we haven't even gotten to yet. I mean, we're really focused on this approach of using pre-existing infrastructure and pre-existing operators to get our CO2 underground safely. And, that's really going to the Permian Basin. So somebody said glide path earlier. I think that's a good term. It's got a lot of runway to get projects done using pre-existing infrastructure. And then again, I think, education is a key piece of earning public acceptance, but so is demonstration. So I think again, there's really an element of novelty to CCS, despite the fact that a few projects have been running for a long time. So I think, collectively onus is on all of us proponents to develop to show that these projects can be done safely. And, if you can do one safely in Texas, you can do one safely in California and try to earn that participation. I think California's got actually a lot of great assets going for it, both to host flue stack CCS projects, direct air capture facilities, novel synthetic fuels. There's a lot of really good ingredients in California, like renewable resource and pre-existing infrastructure and others. So let's hope it's all deployed here sooner or later.
Hi, Shannon Feeney from Open Nanocarbons, and I have a couple questions, depending if there's time. For Jeff's presentation, his slide listed a series of refineries that are California refineries. How many of those refineries are looking at either deploying a CCS plant or direct air capture in augmenting their current refineries and process?
I think I would have to ask, some of my colleagues like George or Deepika to see if they know. What I will say, because I just worked on a year-long study and talked to a number of companies that have California refineries, and they just said it's too hard to do anything in California. I mean, I'm sorry to say so, but I just had direct. They said just give up. We're just going to do it someplace else.
And the too hard is more based on policy and bureaucracy and permitting, or is it
it's just
monetary?
Get pipelines done. I mean, the short version is in the middle of the country where the politics are that nobody believes in global warming. They've got all the great spots to put the CO2 underground. And in California, or Oregon or Washington, where we believe global warming is real and we're willing to pay to stop it, we don't have all those nice handy spots and the handy pipelines. So somehow or other, we got to connect the wires here.
The other question is, and I don't think this was mentioned on the panel at all, but I could be wrong here, is cement. Is cement being looked at from, I guess, a policy standpoint as a physical storage of CO2, basically in a carbonate form? So calcium carbonate, locking CO2 in and attaching it into the rock that's buried in cement is another viable way of storing CO2.
That gets Jen's better, but since I had to go through a lot of this, is the first thing you do to make cement is you take limestone, which is basically God's cement, and you cook it and drive CO2 off. Now you've got lime, which is really reactive. You mix it with some stuff, and then as it cures, it can absorb a little CO2 back. So it did an incredible amount of CO2 out, and then you're hoping to get a little bit coming back in. You can increase it from a tiny bit to a medium bit, by doing special things to inject CO2 into the wet cement while it cures.
Right, that's what
Or wet
Sylvia
concrete while it cures, because it's cement plus some extra rocks is concrete. But the key thing is people are looking at cement capture, but the key thing is you're trying to catch that high amount of CO2 that gets emitted when you cook the limestone. And you got to put that down underground somewhere.
So maybe I'll follow up too. There's a couple of things. So there's looking at reductions from cement manufacturing, but then there's also, I think, something that you may or may not be alluding to, and that is thinking about carbonates as a way to capture CO2, and that's different. And so the idea is you have to be able to find sources like magnesium and calcium, also known as alkalinity, and those are very reactive with CO2. And we've done a lot of work in my group of looking at, well, where can you access that? There's only so much that's actually available out there. We've looked at alkaline residues from cement kiln dust, steel slag from those kinds of facilities, even fly ash in some cases. So there's industrial sourced alkalinity, but again, it's a very small scale, but it exists. And then there's also mine tailings. So looking at mining industries, and there are certain rocks like copper and nickel and platinum metals that are highly correlated to these alkaline species in the earth. And so when you naturally go through those mining operations, the tailings can have high concentrations of alkalinity. And the question is, well, how much is there? And it turns out there's not a whole lot, but there's still great initial projects out there that could get things started at low cost potentially. It's just a matter of how much impact do they all add up to. Then to get to the next kind of level of impact, you have to ask yourself, do we want to start mining alkalinity just to react with CO2? And that is something that's, and there's also in situ mineralization of CO2. So actually injecting it directly into the rocks, like what they're doing with Carbfix in Iceland in the basalts. And so there's a lot of activity in this, and I'm not sure, and Lee might be better to answer, is whether or not, like, for instance, in 45Q, there's a utilization aspect, right? And is CO2, when it's sequestered in the form of a carbonate, and maybe that carbonate is used for road building or construction as a synthetic aggregate, does that fall under utilization or does it fall under sequestration? And I think, too, from the climate perspective, the CO2 has to be stored on the order of about 1,000 years in order for it to truly be stored. And so if, in the case of a carbonate, that's actually pretty solid. So it's a nice utilization opportunity. And I don't know, though, where it falls in terms of 45Q. Do you know?
I was just coughing at your bad pun about the limestone solid. Yeah, sorry.
That was good, right?
I think that's still TBD, given the guidance hasn't been released.
All right, we have time for one, maybe two more questions if they're short.
Okay. So, Saeb Besarati from Idea Lab. I have a question regarding methanol. Because, when we look back in early 90s, we had automobile companies working on making cars that drives based on methanol. And then they stopped working on it. But especially with direct air capture, if we get CO2 out of the air and, through electrolysis, we can make methanol, and methanol can be used as a green fuel for the cars. But to my knowledge, methanol is not considered under the LCFS credit. So do you think methanol should be considered because it can potentially be a fuel that can be used for cars, or no? I think you or Lee, I think both of you.
No, I would just say, actually, I think, I mean, there's some real experts in the room, but my understanding of the LCFS is that if clean methanol were produced and were used in California as a transportation fuel, then that would generate LCFS credits. I think the one other comment I'd make is that, you know, that the pathway that I articulated about using Fischer-Tropsch to go to what's essentially a syn crude that then can be refined into fuels is only one pathway. So if you have clean CO2 and you've got renewable hydrogen or low carbon hydrogen, I should say, you can react those to make syngas. And from syngas, you can go to methanol, you can go to ethanol, you can go FT liquids, you can go to petrochemicals. There's actually a pretty high degree of flexibility there. What was really missing in the past was a technology neutral or fuel neutral policy to pay for it. And now we're really getting into that realm. So I think time will tell, and we'll see what kind of projects can go and what kind of fuels we start getting into the marketplace.
Okay, one last brief question.
Chuck Karupaya from Battery Labs. Question for Keith. What is the minimum size at which it makes economic sense for your system? Maybe in kilowatt, megawatt, or what level of megawatts?
Yeah, we're looking at facilities. We look at them on biomass throughput basis, and 600 tons per day, which would be sort of a 25 megawatt electric power plant when it was running as a power plant. When you make hydrogen from these, you're looking at 5 to 10 tons a day from each site. So the right way to look at it is these are CO2 capture plants that have hydrogen or electricity as a byproduct, because you get some weird incentives. You have to start asking, well, would you prefer higher efficiency or lower efficiency? The lower the fewer megawatt hours or hydrogen you put out, the more plants you then need, and you're just going to pull more CO2 out of the atmosphere. So yeah, 600 tons per day. That would be about 10 tons of hydrogen per day coming off of each plant, and capturing close to 1,000 tons of CO2 per day.
All right.
Will you indulge my question, please? I've had my hand up.
McKinley, go ahead.
Thank you very much. McKinley Addy with ATRA here. So my question is to the gentleman with the two companies, the case studies. California is good at formulating all of these policies, and in my view, have set the market for the low carbon transition. What's been missing are the business models that the companies and proponents of all of these low carbon technologies need to execute or implement to tell a story around, to generate or raise the capital for carrying out the business plan. So if I had $2 billion to give to the two of you right now, what would be a value proposition? What would be a path to scale? And finally, what would be my exit?
Should we split it half and half?
Yeah, okay, that seems fair.
No, go ahead, Keith.
Okay, yeah, and again, we've raised funds for these projects. Our partners are companies like Schlumberger, like Sempra Energy, and basically they obviously have to be profitable. And I had it on the slide, but I had to kind of rush through it. We have 3 revenue streams: hydrogen, LCFS credits, and 45Q tax credits that have to be structured. The hydrogen has to be sold at commodity price, or the refineries won't buy it. There's talk about premiums on green hydrogen that will work for some markets, but when you start talking about tens of tons per day, then you need to be able to get it to the refineries, and they're going to say, well, I can make it from natural gas, I can pay a carbon tax on that, and this is my price. So the model works because the value of capturing CO2 went from that $20 to $250, and we're below $100 is what we need. So we run the models, we show the sensitivities on it. All of the equipment is off the shelf and commercially available. You need fixed price engineering contracts on it. We can get that. And our equipment has been running for thousands of hours, and we can get performance insurance on our equipment. So basically it looks like classic project financing, and the exit is either the returns on the project, which are attractive, or it can then be sold to pension funds, institutions, or insurance companies and longer term investors once it's up and running.
Yeah, I like the question. It's very entrepreneurial, and frankly, I've got colleagues who are bit more positioned to answer that from the financial perspective. But I think what I'd say is just, I think we're all pretty used to environmental projects having to compete and win on other merits. So like cost savings or cleaning up criteria, air pollutants, and somehow they had to be cheaper than the incumbents, or they had to do something else that was of value. And I think, you know, again, with the evolution of the LCFS and the CCS protocol and the implementation of 45Q, we're going to run this Permian project on the oldest value proposition there is, that if you lend us money on a debt deal or an equity deal, we're going to return it to you with interest in the case of debt or an IRR in the case of equity. And frankly, the cost stack, we're going to get the revenue stack built up so that it's higher than our cost stack, and the margin is what we pay our investors back from. So it's really about getting investor classes and financial markets more comfortable with 45Q and with LCFS as dependable revenue streams. And I think that's what I was alluding to earlier, you know, in saying that we still collectively have to refine these policy tools and have to refine how we use them, how we get financial markets comfortable with them. You know, just to throw out a couple of examples. I mean, we talked earlier about credit offtake, you know, and the challenge there without some kind of price guarantee or some kind of price floor. You know, those are levers that can be pulled. I think we're still all collectively figuring out how to comply with and implement the CCS protocol. And you know, some of I mean, there's a bunch of incredibly smart and sensible criteria in there to ensure permanence. But I think we all have to look at that and keep reevaluating it as we get projects in the ground and we learn from them. But no, to come back to your question, I mean, it's simple costs and revenues and a margin and a return to investors.
All right, well, with that, we are going to close. I want to thank our panel. Let's get a round of applause for them. So the materials for this workshop will be posted on our website on the Carbon Neutrality Workshops page, and a recording will be available sometime next week. Thank you.
All right, ladies and gentlemen, I am a contractor. This room is going to be set up at 5 o'clock. If you could take all your conversations out of the Byron Share Auditorium into the foyer, that would be wonderful. Thank you.